Ora si registrerà la conferenza.
Another example here from 2016, where there was a situation with very cold temperature extremes over North America. You see them in the bottom right part of the figure, and very strong winds and storm activity over Europe, bottom right part of the figure. So this seems to be anecdotally sort of a recurring pattern, that you have very cold extremes over North America and then storm activity, wet and windy, over Europe. And people have noticed this, but they have analyzed these two sets of extremes separately, typically. So on the one hand, cold spells over North America, on the other hand, storm seasons over Western Europe. And what I've tried to do with my work in the last couple of years is really make the connection between these two sets of extremes. And the first step has naturally been to test whether there is systematic co-occurrence. So was 2013-14, this winter I just showed, and the other example from 2016, just random co-occurrence, sort of freak events, or is there really a significant and systematic co-occurrence of cold spells over North America during winter and wet and windy weather over Europe? And as you may guess from this presentation, the answer is yes, there is such systematic co-occurrence. Having established that there is some statistical co-occurrence, the next question is naturally whether we can identify a physical pathway connecting the extremes in these two remote regions. It turns out we do identify some large-scale atmospheric configurations which favor the co-occurrence of extremes, but it also turns out that there's actually not a single atmospheric pathway, but at least two which favor the occurrence of these compound extremes. Finally, there's been some work in my group looking at synoptic scale dynamics. So how do these large-scale patterns actually relate to cyclone activity, which is what concretely gives the European extremes. In the interest of time, to keep to the 25 minutes, as Simona asked, I will skip over this part, but if anyone is interested in the synoptic scale analysis, then I'm more than happy to discuss it further after the presentation. So, first things first, the first step when studying these pan-Atlantic extremes is naturally to show that they are a thing, namely that there is a systematic co-occurrence between cold spells over North America and stormy or wet and windy weather over Europe. One can start simple, just make a climatology. So in the bottom part of the figure here, you see a composite of surface temperature anomalies over North America conditioned on European windstorms. And what this shows is that when there is a windstorm in Western Europe, it tends to be anomalously cold in North America. While in the top, you see in blue an index of severe windstorms in Europe. This is computed as a destructiveness index. It's not very important here. But the blue curve is an index of severe winds in Western Europe, and the green curve is an index of precipitation in Western Europe. And so you see that these are lags relative to cold spell days in North America. And so the main take-home message here is that both these lines are above their climatology, which is these thick lines, and often above a 95% confidence level, which are these dashed lines, around the time of the cold spells. So it really seems to be a bidirectional link. If it's cold in North America, it tends to be wet and windy in Europe. And if it's windy in Europe, in this case, you can do a similar thing for heavy precipitation cases, then it tends to be anomalously cold in Eastern North America. So far the story holds. You can actually do this in a bit more of a systematic way. And one can look at composite anomalies of sea level pressure, here shown in contours, 2-meter temperature, and total precipitation in the top panel, and 10-meter wind anomalies in the bottom panel. And so here what you see is temperature anomalies over North America. So you see blue, it means they're cold. And top panel, total precipitation, and bottom panel, 10-meter wind anomalies in Europe during a set of pan-Atlantic cold, wet, windy extremes. So here we really see this pattern of cold eastern North America and then wet and windy Europe, roughly the wet and windy extremes occurring in the same region. And you also see from the sea level pressure composites that there seems to be some systematic anomaly structures here. So there is a clear signal that something is going on at large scales when these extremes, or rather when these events, because here I'm not specifically looking at extremes, co-occur. Now we can actually focus specifically on extremes, because so far I've showed sort of these climatological composites. They show large anomalies, but the large anomaly doesn't mean that it's really an extreme event. So now here I really consider the extremes. And what I'm showing in these two panels is normalized frequency of extremes. So regardless of how you define the extremes, 1 means that it's the frequency you expect from your definition. Numbers above 1 means that, so in the red, means that you have a lot more extremes than you would expect given your definition. And this is just one example for a specific set of cold spells in North America. Obviously, you can define cold spells in different ways and over different regions. But this is a specific set of cold spells that, for example, gives a good 10-meter wind extreme signal over Iberia. And so in this case, we can say that there seems to be a statistically significant link between cold spells over, in this case, central United States in North America, and a significantly increased frequency of 10-meter wind extremes in Iberia. An interesting point here is that this seems to be a very regional signal, right? For example, we see nothing over central continental Europe or Scandinavia or the British Isles. So this already gives us a hint that this statistical link exists, but perhaps is more complex than just saying cold spells somewhere over Eastern North America, and we'll definitely get extremes over all of Europe. And this is an attempt to summarize this regional link. So what we see here is pie chart. This is a map of North America. The pie charts are placed over different regions where we define cold spells. So we just take a box and sort of shift it around the continent. And the colors of the pie charts show which regions in Europe display wind extremes when there is a cold spell at the location of the pie chart. And the stippling means the link is statistically significant. And so you can see that there are some very clear patterns emerging. For example, Iberia tends to be affected by wind extremes and anomalously high frequency of wind extremes when there's cold spells in the southern western part of North America. British Isles tend to experience very many wind extremes when there's cold spells over eastern Canada, et cetera, et cetera. So you see that there is really a clear regional structure to this link. And depending on where the cold spell is, you'll see different downstream wind extremes in Europe. And you can do the same thing for precipitation. And so in this case, it's exactly the same thing as before, but looking at precipitation extremes. And you see if I flick between the two, that the patterns change. So not only is the link regionally dependent, but we also seem to have slightly different regional dependence depending on whether we are looking at extreme wind over Europe or extreme precipitation. So this essentially suggests that there is a statistically significant link. We can look at cold spells over North America and wet and windy extremes over Europe as a joint set of compound pan-Atlantic extremes, but that the link is variable, regionally dependent, and dependent on whether we focus on wind extremes or precipitation extremes over Europe. Moreover, the fact that we have a statistical co-occurrence obviously doesn't mean that we have causality. And so here I would just like to highlight that you can reproduce the plots I just showed for different lags relative to the cold spells over North America. And you get slightly different results, but strikingly, you often get European extremes before the peak of the cold spells. And so this suggests that even if there is this statistical link, we should not regard the European extremes as a sort of downstream consequence of North American cold spells. Perhaps there are slightly more complex dynamics at hand. And so just to summarize, these are the main statistical links we see. So for cold spells over eastern Canada, we see increased wind extremes over the British Isles and Northern Europe. If we move to eastern United States, southeastern Canada, we observe both wind and precipitation extremes primarily over Iberia and southern Europe. And if we look at cold spells in the central eastern part of North America, then we again see a footprint in Iberia for both wind and precipitation extremes. But in this case, the interesting thing is that this footprint is strongest at negative lags relative to the cold spells. So to some extent, the extremes in Europe seem to precede the peak of the cold spells in North America. So there is this complex statistical link. How can we relate this to large-scale dynamical processes in the atmosphere? And there are several open questions. So first of all, a general one about the dynamics, a second one on whether there is a systematic response of the North Atlantic storm track to cold spells in North America. That can explain then the extremes in Europe. And a third question is if the extremes in Europe sometimes precede the cold spells in North America. Is it as simple as finding a systematic set of anomalies in the North Atlantic storm track? Or is there some more complex process going on? One can also wonder then, is there a role for signals coming from the Pacific? So there's really a lot of open questions when looking at the dynamics of these compound extremes. Again, start simple. Just look at composites. So here on your left-hand side, you see composites of upper-level zonal wind, and on the right-hand side, it's upper-level geopotential height anomalies. And this is for a domain in eastern North America, just to illustrate one case, so cold spells over eastern North America. And you can see this very striking pattern from 5 days prior to the peak of the cold spell to 5 days after. There is this very striking pattern of an intensification and a zonalization of the North Atlantic jet. And this is coincident with a wave-like structure in the geopotential height field, which is suggestive of wave propagation from the Pacific towards the North Atlantic. And there's some minuscule arrows here that you can't really see, which are Takaya-Nakamura wave activity flux, and the convergence pattern of the wave activity flux is consistent with an intensification of the jet stream over the North Atlantic region. And this is just a similar plot, but for different regions, cold spell regions in North America. One in eastern Canada, one in central Canada, one in eastern United States, the ones I showed previously. And you can see that there are differences in this is again upper level zonal wind. There are differences in the location of the anomalies, but in all three cases, when you have a cold spell, you have an intensification and zonalization of the jet. In some cases, further to the north, in some cases, further to the south. In some cases, it extends more to the east. In some cases, it is really limited to the North Atlantic. But this general structure of a zonal intense jet holds for all three sets of cold spells you consider here. So there seems to be something whereby the cold spells, probably by increasing baroclinicity, when cold air comes in contact with the North Atlantic, seem to favor some response in the storm track here. And then the question is this a systematic thing? So do we see the same pattern for all cold spells in a given region? And this is normally the expectation, right? When you look at a given set of extremes, you do a composite, you check the variance of that composite or something along those lines, and you sort of expect that you have one driver of a set of similar extremes. So if the surface footprint is similar, then the set of large-scale drivers should be similar. And this is an example for the central USA cold spells. This is wave activity flux you see here in the vectors, and the colors show stream function anomalies, upper level stream function anomalies. And the purple contours show upper level zonal wind anomalies. And so here you see for the central USA cold spells, you have a wave train coming in from the North Pacific. At lag -4, you have some signal of intensified jet over Europe already. Then the cold spell progresses. These are always, I remind you, lags relative to the peak of the cold spell. You continue having this incoming Rossby wave propagation from the North Pacific. You continue having some signal of intensified jet over Europe. But at the same time, you start seeing this new signal of an intensified jet in coincidence with the location of the cold spell. At lag 0, the signal over Europe actually disappears, and the jet anomaly that originated in the vicinity of the cold spell extends across the North Atlantic. And this is a bit puzzling, right? So it seems that you have a signal at negative lags over Europe of intensified jet, and then sort of this thing seems to start again with an intensification of the jet around the cold spell region, and then this extends again towards the North Atlantic. So there seems to be something that isn't quite working here. And so what we did is that we tried to separate the cold spells in this region. We said, well, maybe even though the cold spells at the surface look very similar, they could be associated with different large-scale drivers. And so we separated the cold spells according to the signal of wave activity flux coming from the Pacific. So we defined a set of cold spells with a strong wave activity flux from the Pacific and a set of cold spells with a weak wave activity flux from the Pacific. And we tried to see whether they were different to try and explain this odd European signal at negative lags. So this is the set of extremes with a strong signal from the Pacific. By definition, you see this strong wave propagation from the Pacific. This is the region of the cold spell. And you see that there is no jet intensification signal over the North Atlantic before the peak of the cold spell. Then once the cold spell peaks, you see a very, very clear signal of jet intensification. So this really seems to be a sort of a causal sequence. Strong wave activity propagation from the Pacific, cold spell, jet intensification over the Atlantic. If we pick the set of cold spells with weak wave activity flux from the Pacific, obviously there is a weak wave activity flux by definition, but we see that the jet is already intensified and zonalized and displaced southward before the peak of the cold spell. So this is sort of a pre-existing structure, atmospheric structure. So these purple contours again mark an intensified jet stream. And then this continues at day 0 when the cold spell peaks. No big change as the cold spell evolves essentially in the jet structure. And this is just a comparison of all cold spells in this region I just showed. Cold spells with a strong wave activity flux from the Pacific, cold spells with a weak wave activity flux from the Pacific. Blue shades are temperature anomalies over North America in standard deviations, and the red shades over Europe are occurrence of extreme wind events. And so you see that the case with the weak wave activity flux, where the jet is already zonalized and intensified prior to the cold spell peak, has wind extremes over Europe at negative lags, while the case with the wave propagation from the Pacific and subsequent jet intensification has wind extremes over Europe at positive lags following the peak of the cold spell. So what have we learned? Well, the hypothesis then is that a very similar, seemingly similar set of compound extremes can be due to two very different pathways. In one case, we have a propagation of a Rossby wave train from the Pacific. This favors the occurrence of cold spells. If you actually look at the geopotential height over North America, this seems to be an Alaskan ridge type configuration favoring cold air advection from the high latitudes. This modulates the North Atlantic storm track, stronger, more zonal jet. One gets wet and windy extremes in Europe, so sort of a causal train of events. Then there is a second case where you don't really have any signal coming in from the Pacific, and it seems to be more a case of an Atlantic preconditioning. So you have a set of pre-existing conditions over the North Atlantic, and these seem to be associated with cold air advection over North America, giving a set of cold spells, and an already intensified and zonalized jet prior to the peak of the cold spells, favoring wet and windy extremes in Europe. And so in this case, the link isn't really causal between the two sets of extremes, but it's more statistical in the sense that there is a common driver, but then there is no causal link from the cold spells to the wet and windy extremes. So the European events are not a consequence of the North American extremes. And this is just a summary schematic. So in one case, Pacific signal downstream effect on Europe, this purple arrow being the jet stream. In the other case, a sort of preconditioning which favors the roughly simultaneous occurrence of these two sets of extremes. So here I focused on a very specific case, namely wintertime cold spells in North America and wet and windy weather in Europe, extremes in Europe. So a very specific case of compound extremes. I've shown the two sets of events co-occur statistically. I've shown that we can identify large-scale structures which support physical connection between these extremes, but that the connection is not always a causal one of the European extremes being a downstream consequence of the upstream North American cold spells. So in some cases, it may be a matter of a common precursor leading to the concurrence of these extremes. And that the link between the extremes is quite variable on a regional basis. But I think this specific example actually raises two interesting points that are more general and applicable to the study, to the broader study of extreme events and compound extremes specifically. One of them is that sets of extremes with very similar surface footprints may not necessarily be associated with a single driver. So just because they look similar at the surface, we shouldn't assume that what we see in the composite represents a single physical driver. We can have very similar surface extremes, but quite different large-scale atmospheric drivers. So this is, I think, an interesting generalizable point. And the second interesting point is that there's been a lot of work on waviness and extremes. And I know, for example, colleagues like Kai have done some very interesting work on this point. But in some cases, it's not only the waviness that does it, but also the lack of waviness. So in this case, the zonalization and intensification of the jet. So it's certainly important and interesting to understand how waviness can lead to extremes, but we shouldn't think that waviness is the only mechanism that can link remote extremes to one another through a physical process mediated by large-scale atmospheric motions. And with this, I think I've more or less used up my allotted time, so I think I'll leave you with some references and stop here.
Great. Thank you so much, Gabriele, for your it was a great start of this workshop, and also thank you for staying perfectly on time. So it's time for questions, and I think maybe we can start from questions here in the room, and then we'll ask people online if they have any questions. Any questions for Gabriele? Maybe can you just introduce yourself so that your name.
I hear that someone is speaking, but very, very far away. Maybe Valerio or Simona, either they come up or you repeat the question, whatever is easiest.
Giuseppe is coming up.
Ah, it's Giuseppe. Okay, I haven't even recognized the voice.
Hi, Gabriele. Great talk. I was wondering if you looked which one of the two types of cold extreme connections is more predictable, whether there is any difference on whether you have incoming Rossby wave forcing or not.
Yeah, so that's actually, that is a very good question and such a good idea that it's actually the topic of the work of a new postdoc that recently joined the group, and I totally agree. We should be looking at this, because one may imagine that if there is this sort of causal propagation from upstream to downstream, naively it could be easier to predict. One may have longer predictability timescale, especially for the European extremes, than if there is this sort of preconditioned North Atlantic atmospheric structure. So we haven't, but that's part of our current plans, and it's definitely would be interesting to look into this further.
Please. Yes, please. Yes.
You can come
Say your
close.
name so that they know who you are.
Hi, Kai.
Really nice talk. So my question is, and maybe you mentioned this, sorry if I missed it, but that goes into a similar direction, but regarding the persistence of these types of drivers that you identified, is there anything that can be said about this? The persistence of the events?
So what is the question? How persistent the drivers are, or how persistent the actual cold spells are?
I mean, the impacts of cold spells there relate a lot to like how long they last, right? So I was wondering if, yeah, these two different causes can also be distinguished in that respect.
In terms of persistence of the cold spells. So there we haven't looked at that in the sense that in our definition of cold spells, we sort of build in a minimum persistence requirement, because we separate the cold spells. So we ask that they're separated by at least 10 days, I believe. So we are sort of only focusing on cold spells that are already quite persistent on sort of a weekly or longer timescale. So in that sense, we would need to, it's a good point, but we would need to redefine our cold spells to also include shorter lived ones to really be able to make a statement about their persistence.
Step back.
Hi, Gabriele and Melinda here. Really nice talk. Hi. My question is, so you kind of identified two different causality structures, basically. So one is this rather sequential causality, where for the high reactivity flux events, when like you kind of the disturbance propagates and affects the exchange over Europe. And then the other case is then where you have kind of a common source, and then the cold spells over North America and the wet and windy extremes over Europe are caused by this common source, right? Yeah. So I was wondering if we have any idea what is this common source causing the two extremes over North America and Europe?
Yeah, so the short answer is no. The longer answer is that we looked at the usual suspects. So, you pick indices of variability modes, that sort of thing. And we don't really see a strong projection on anything, to be honest. So it's not as though we can say, it's because it's a combination of, I don't know, NAO and PNA or whatever. So there's sort of this pattern here. So there is it resembles to some extent a negative NAO, but doesn't really match the geographical location or structure, nor of the Arctic oscillation. So we weren't really able to relate this strongly to any known variability mode. And then the question is could it be the remnant of some previous event, or not? And we don't really have a good answer to that yet. So if anyone has any ideas on this point, they are most welcome.
Thank you. Maybe one last question, and we'll see if there is any questions from the audience online.
Hi, Gabriele, it's Emanuele Bevacqua here. Thanks for the talk. So two quick questions. The first is about what's the sector that gets affected by this concurrence of extreme events. Maybe it's related to insurance company, I guess. So whether there are some effects, let's say, that leads to particularly high levels when you have this concurrence. And then the other one is about whether you are planning to look at whether these causal paths are well represented in climate models, or if you have already looked at that, basically. Thank you.
So concerning climate models, we have a PhD student in the group now that is downloading a good chunk of CMIP6 models to look at this. And so the idea is to, I mean, CMIP6 models have become better than CMIP5 ones at things like jet tilt and jet strength, but it's not obvious that they can necessarily all well reproduce these very anomalous zonal southerly shift jet configurations. That's something that will be interesting to verify. Concerning the impacts, it's mainly, I would say, insurance companies, in the sense that for their financial purposes, they consider these sets of events as completely independent. So they're not accounting in any way to having potentially a big payout in the US or Canada at the same time as a big payout in Europe for a completely different type of hazard. So they would probably be the ones most interested in the concurrence of these events.
Okay, great. We just want to make sure that we also, if there is questions online, we have time for just one quick question. If there is one, please let us know online. Maybe put it either on the chat or just open your microphone and speak.
I have one question. And hi, Gabriel, for nice talk. Thanks for the nice talk. Can you hear me?
Yeah, loud and clear. Thanks.
Yeah. Okay.
Fabi.
Yeah. Thanks. Hi. So my question is about, in one slide you show like the jet, and you show geopotential height at 500 heptapascal and 200 heptapascal, and then you also mention about the Rossby wave. So my question is it Rossby wave related to tropospheric jet, or is it related to stratospheric jet? Like, what exactly it is related to, like why we do the Ross wave analysis rather than just understanding by analyzing the geopotential height? Okay.
I mean, on the simplest level, you can see these wave activity fluxes as telling you sort of the propagation of energy or information, basically, in the atmosphere. That's a way of interpreting them. So I think they provide a good complement to a purely composite analysis like you would do for geopotential height. I mean, if you just do a geopotential height composite, it doesn't tell you where stuff is going or where energy or information, which is one interpretation of energy, is flowing in the atmosphere. So I think in that sense, studying wave activity and wave propagation provides an additional insight. And also the divergence, convergence of these wave activity fluxes can tell you something about, or can help you explain whether you're fluxing momentum into the large scale jet or not.
Okay, so it's like kind of just the matrix to support what we get from the geopotential height. I don't know if
I would see them as, two complementary pieces of information, and when you put them together in a single plot, then you get a more complete picture of what is going on.
Okay, thanks. Because this is what I missed in your talk. I didn't understand like what is the methodology to compute the Rossby waves. So okay, thanks.
I mean, in this specific case, I used the flux from Takai and Nakamura. I think it's 2001 Journal of Atmospheric Sciences. So it's a relatively widely used flux measure. It's nothing I invented myself.
Thanks.
Okay, great. Thank you so much, Gabriele. We need to move on, but thanks again for starting off our workshop with such a great talk. And so now we have Jacopo Riboldi, also a keynote speaker. So one question, we heard that you guys in the back are having a little bit of a hard time understanding the speaker. Is it true? Well, first of all, there is space, so you can move ahead. There's plenty of space. We're gonna try with the next speaker to raise the volume. I'm not sure if this is working. But okay, but I'll give the floor to Jacopo. Maybe I'm gonna sit so that Jacopo has space
Yes.
here. And I'll be back.
I'll take care of
I'll
the
give you a
technical
warning
stuff.
if you need it.
And yeah, so let me open your slides.
Sorry, can you say the title of your talk because I didn't say it?
The title of my talk is, I don't remember it, I have to see it on slides. Oh, circulation persistence and presence of Rossby waveguides during heat waves in the Northern Hemisphere. Long title. Next time, shorter is easier to remember. Maybe. But yeah, thank you very much. First of all, welcome everybody. First of all, I wanted to. Can you see my slides?
Can you see the slides remotely?
Yes, yes.
Great, thank you.
I see the PowerPoint though, not the full screen.
What about now?
Still the PowerPoint. I mean, it's not a big issue. I can live with seeing the screen, but
Because we are seeing the
full
screen. Okay.
And sometimes it's a matter of when you do the screen sharing, there is sometimes the option to choose also the presentation. It's a bit tricky. I also had this problem last time.
So let me try again.
Yeah, second one. See the first, yeah.
And then no. Wait, maybe here.
Maybe you can do that. Maybe it's good enough.
I mean,
perfect. Is it better, Gabriele?
no, we still see the PowerPoint, but for my part, it's fine. Don't worry about it. I mean, I still see everything. So.
Okay.
Okay. Anyway, then again, welcome everybody. First of all, I wanted to acknowledge the contribution of Emanuele Russo and of Christopher Polster from ETH Zurich and the Johannes Gutenberg University in Mainz. They provided data. They did some plots that are here in these presentations, and we had a lot of nice discussion in the last 2 months. So, yeah, thank you very much, and I hope that it will also be interesting for you. And also, yeah, thanks also to the organizers of this workshop, which is very timely, and it made me think to this review paper that just was out last year, the paper by White et al. The title is From Atmospheric Waves to Heat Waves, waveguide perspective for understanding and predicting concurrent persistence and extreme extratropical weather. It really fits with the title of the workshop here, and in this talk, I will also try to adopt then, in the spirit of this paper, a waveguide perspective, and you will see how we can try to connect Rossby waves and extremes using waveguides.
I think that they cannot see.
They cannot see. Oh, then you have to.
But now they can. That's interesting. Oh, okay. So I guess that if we are not on live screen, then they can see this the screen changing. So that's the interesting part. So we should also stick to PowerPoint.
Okay, it's just that then the animations would not appear as nicely, but.
You can just stop sharing and turn it again. And
Yeah, sometimes it's a bit tricky because wants to share the full screen, but it's tricky to do it also. The weather discussion sometimes. Yeah, exactly. So,
yeah.
shall we? Yeah.
No.
Okay, this maybe also works. Does it?
Yes.
Is it better?
Now it's full screen.
Yes, perfect. Good. Thanks.
No, now I see. Oh yes. Now I also see the new slide. Super.
Perfect. Thank you. So, yes. So we will talk again about Rossby waves and heat waves, about waveguide diagnostics, and then after this introductory part, I wanted to show you an interesting set of results that we just somehow we're working on that with Christopher Polster, and essentially it's an application of his diagnostics of waveguide to 2 heat wave cases, one in June 22 and another one in the 2010 Russian heat wave. And I will skip some slides for the sake of time because I want to have some time left at the end to talk about these results. So, which I think I hope they will interest you. But yeah, Rossby waves are connected to heat waves. That's one reason why we are here. And there is a direct impact of Rossby waves on heat waves, which has been discussed for instance, in this recent work by Rossby and Papritz. This direct impact can be divided in three parts: the horizontal advection of warm air by the Rossby wave circulation, the subsidence related to the descent in the anticyclone, which warms the air masses, and also the fact that we have clear skies in an anticyclone, and this is due to the descending motions indeed. And the clear sky allows for solar radiation to penetrate the troposphere and warm the soil, dissecate it, and lead to it's an important driver of the soil moisture feedbacks. And with this tool, we can really try to dissect an heat wave like Rossby and Papritz did, and to understand which process contributed the most to the observed extreme temperatures. And besides this direct effect, however, there is also an indirect effect of Rossby waves, which is more related to the reason why a heat wave comes along, why it starts, why it persists for so long. And Rossby waves play also a role in that, because the persistence of the large-scale circulation is due to the large-scale flow configuration. And Rossby waves are an integral part of that. A typical example is one of atmospheric blocking and the maintenance of atmospheric blocking by transient waves, by dry and moist processes. Here I put a nice schematic from a paper by Ali et al. 2022, Weather and Climate Dynamics, where they try to assess the contribution of Rossby waves to the maintenance of blocking and heat waves over Southeast Australia. These story somehow of Buddhist waveguide boils down to the original, to the initial assumption that we do when we study Rossby waves, that there exists a background flow separated from the waves. And this background flow has the waveguide in it because it's kind of the environment in which the waves propagate. And this waveguide can be seen as a meteorological entity that allows to duct Rossby waves along a preferential direction and preventing the energy loss that always happens towards the equator. There is not a waveguide, but limiting at least this energy loss. And this waveguide has to persist for a longer time scale than the waves it carries. However, the definition of that can be a bit tricky. And here I try to build up to one example to show you why this can be tricky. Let's take a first case. Imagine this on a polar diagram when we have a stationary wave. It means that the troughs and the ridges are fixed in longitude, and if we plot them on a polar diagram, they just appear always like at the same longitude indeed. And here, if you have an heat wave during this dynamics, our question is, okay, what is making these waves stationary? Why they are not propagating? There is a blocking, maybe the large amplitude at large scale prevent propagation, resonance. And now we can also observe a similar persistence if we have a situation of recurrent traveling waves. So here we have imagined a series of different Rossby wave trains that, however, have always the same phase. And here the question is different. It's not, these waves are not stationary. The question is why they are forming always the same location and they are propagating in the same way. And so maybe there is a waveguide, I don't know. But you see, the types of questions we ask ourselves depends on how we look at the waves, which waves we are considering. And this pathological example is actually not so pathological because recent research has shown that this type of waves exist. These are the recurrent Rossby wave packets. And here's an example of two cases, one in autumn and one in winter. You can see with the dashed black lines that the individual wave packets were traced. And you see they occur more or less always in the same location, and in both cases, it's quite remarkable. And if you apply a time filtering, so we do a time averaging, essentially a block of 10 days, for instance, the result is that what is left is something that looks like a stationary wave, if it's obviously constant longitude all the time. But these are not stationary waves; these are traveling waves. So we have to be mindful when taking time averaging. We risk to misunderstand the waves and so misunderstand also the research questions we want to ask ourselves. And these waves have also been shown to be significantly related to an enhanced persistence of hot extremes. Here we see the regions here where there is warm colors here indicate an enhanced length of warm spells with respect to the climatology. And this is, I think, is very fascinating because it's quite counterintuitive that the persistence of the weather is resulting from an enhanced activity of transient waves. You have a lot of transients, but the weather is not transient; it's persistent. And this reminds me also of a paper that is now in discussion on weather and climate dynamics. It's a WSID idea. So again, in the spirit of the workshop, discussion is open and welcome, and where Clemens Kensberger tries to argue that this mechanism, this mechanism is able to explain the teleconnections we observe across the world somehow, and not through stationary but through transient waves. And it's a nice perspective. If you're interested, I can recommend you to take a look at this short paper. I also wanted to close the introductory part with a little discussion on waveguides and blocking. When we have a waveguide, we have a clear separation, as I said before, between the background flow and the waves. The waves propagate along this background. The background is unperturbed while the wave propagates. When we have a blocking, which is, on the other hand, a very amplified wave that behaves non-linearly, this clear scale separation is lost. We're not having anymore the waveguide and the wave, because the blocking itself evolves on a time scale that is low. And so by time averaging, again, it's difficult to disentangle the two. And when we talk about, there is some how to say, confusion about the role of waveguides in blocking. Is the blocking a part of the waveguide, like a degenerate wave, but it is still part of the waveguide? As, for instance, the traffic jam model suggests, the one by Wang and Nakamura with local wave activity? Or is the blocking an external somehow entity to the waveguide, which is able to redirect the waveguide in different regions, create new ones, displace it? And this is like the split jet configurations that we observe during blocking, etc. It's not so clear, yes, if the interaction of waveguides with blocking. It's an open question. And I will show you later, however, a result that is nice on that, I hope. And in terms now, let's go maybe a bit more in detail and talk about waveguides. I took a paragraph from the review paper by White et al. I said at the beginning. And they say in this that there are two main ways of defining the waveguide once we have defined the background flow unambiguously: the refractive index way and the PV gradient way. For the sake of time, I will not read why exactly, but in this paper they argue that the PV gradient approach should be regarded as superior as the refractive index one, and this is the same approach that we will see now in the rest of the talk. But the refractive index has this issue that it's either there or not there, while the waveguideability is something that looks more continuous rather than a step switch, which is there or not there. And one of the problems with time averaging is that it often carries the, I start again. The background flow should be wave-free. It should not carry any signature of the waves. But if we do if we take a time averaging, very often we are not able to eliminate completely the signature of the wave onto the background flow. And this is a pathological example built by Wirth and Poster, 2021, by creating this couple of vortices that resembles like Rx blocking. And if we take a zonal averaging and a time average, this is actually a zonal averaging and a time averaging, and we see that we obtain a double jet structure. But this double jet structure is mostly there because of the fact that this simple approach is not able to disentangle the wave from the background flow. And there is the ray tracing approach by Hoskins and Caroli, for instance, but is based on the WKB theory, which requires a slow variation in latitude of the background flow compared with the scale of the waves. So the flow should vary slowly in latitude and in time. But this is not true when we have large-scale configurations. So after I've said a lot of negative things, let's try to get in the right background flow so that we can use the gradient of PV to get the waveguides. And one of these methods is, I call it isentropic rearrangement of potential vorticity. Has been proposed by Nakamura and Su in 2010, but also again by Metfen and Beresford. It's all based on, as the name says, indeed, an isentropic rearrangement of the potential vorticity, like on a certain isentropic level, so that the troughs and the ridges are straightened up and they become more like a zonal contour. And the idea would be to find an equivalent latitude that can contain all the PV encompassed by a certain isoline after having removed all the troughs and the ridges, so that the area in the D1, the pink area in the plot in the middle, is the same to the light blue areas in the plot to the right. So we identify this latitude for a certain PV contour, then move to another PV contour, which is a bit lower, and we obtain another latitude, which should be a bit lower, because PV increases with latitude. And in this way, you obtain a zonally symmetric background flow, like a series of volts, like PV volts all around the North Pole. And the problem of that is that this procedure is quite complicated, because if one wants to do it right, we move the potential vorticity, we are conserving the PV and the theta, but we are changing the stability. So one has to do it iteratively with a lot of PV inversions, so that we are sure to create a field that is in balance, both in terms of circulation and in terms of mass. So it's quite demanding. And I don't go into details indeed, because it's very complicated. You can read the Metfen and Beresford for 2015 if you want to understand a bit more. And yes, the idea, as I said before, is really to, if we have a pathological, again, I add these overturning contours, we can straighten them by moving the trajectories from high to low latitudes and sort them with respect to PV values from the pole to the equator. Now it comes Christopher, who really collaborated a lot on that. During his PhD, he found a way to simplify this isentropic PV rearrangement so that it can be applied in a fast way to a flow that is complex, and that we do not obtain simply a volt, but we obtain a background state that resembles somehow the actual flow in a certain day. Because the background flow is not always fixed. It can change very slowly with respect to waves, but it can change both in latitude and in time. And here there is an example to explain you how it works. So here we have PV distribution, this potential vorticity at 330 Kelvin. It's again as this overturning contour, so there is a blocking over the North Atlantic. You can see it here. You can see also the meridional wind anomalies. And the idea would be to apply this zonalization on a rolling 60 degree of longitude window. So we take the first 60 degrees, we rearrange the PV in there, and then we attribute the profile to the central longitude. Then we move it, we then move it of 1 degree, etc., etc. And in this way, we're able to obtain a background flow that's very slowly with longitude. And the result is the one you see here on the right. We see in black is the PV contour of the initial field, and in blue you can see now the zonalized background state, which has a certain PV gradient. And if you compute the PV gradient, is the plot down the letter F, we can see that it follows more, it goes somehow through the waves. You see here, for instance, over, I don't know if you can see my pointer, but here across the US, it goes through these trains of ridges and troughs. And also here, it gets weaker where there is the block. The PV gradient decreases here. While if we just take the temporal average, so this is the 14-day, 2 weeks time average, we do not, and then we compute the PV gradient of this field, we still see that the PV gradient retains some characteristics of the waves. For instance, this wave here that we see over California, more or less, it doesn't look like a background. This looks like more like a wave structure, and so it's not as good as the usual time filtering is not as good at removing the waves from the background. And now comes actually start with other results using this methodology, which will be like the rest of the talk. So here we see the climatological. So this is a waveguide frequency. Essentially, we say, okay, we have a waveguide when we have a value of gradient of potential vorticity, the logarithm of potential vorticity actually, larger than a certain threshold. The threshold is relatively unimportant. And so if we have a value larger than this threshold, we say waveguide yes. and we count it. And here we have a map of waveguide occurrence frequency on the isentropic level of 330 Kelvin during winter, and some PV contours in black. We see at this level, we have the waveguide that goes mostly over a bit over North America. We see it here in the North Atlantic, and then we see the subtropical waveguide south of Tibet. But this is the nice thing is that we can see how this waveguide changes with respect to the season. So at 235 Kelvin, for instance, I'm comparing here 2 months, June and December. And in June, the waveguide is more displaced to the north, this isentropic level, while in December is more displaced to the south, similar to the plot that we saw before. So this waveguide changes with the season. It changes with height, depending on the isentropic level we're considering. 225 Kelvin, we find the waveguide quite at the north, and at 345 Kelvin, on the other hand, this is again for June, we see the tropical waveguide. So depending on the chosen threshold, on the chosen, isentropic level, we can find different waveguides. And at 235 Kelvin, there is maybe a bit of both. But then you may wonder, okay, we have these waveguides everywhere. Is there really a waveguide? Yes, there is. I think there is something, because if we take a certain grid point, you can try to quantify for how many isentropic levels we are having the waveguide. So for instance, here over North America, these points here, we have this dark green. It means that we fulfill the waveguide criterion over a depth of 20K, 15 to 20 isentropic levels, which means, okay, in these points here, the waveguide is located at the same location for many isentropic levels, and we expect it to be then able to duct the waves in an efficient way. And I will show you now some animations, and you will see better what I mean with that. But if we have to summarize a bit also the limitations that this method has, it's dependent on the threshold, of course, because we have to specify when we say waveguide yes or waveguide no. And this is as an arbitrary choice. Also, it depends weakly on the width of the averaging window. 60 degrees seems a bit optimal, according to Christopher at least. Also, given that it's a simplified approach, it does not require the PV inversion. The PV is not exactly conserved. Well, the PV of the whole zonalized state is not exactly conserved with respect to the initial somehow snapshot we started with, because yeah, there is some mismatch. We have to usually we try to solve it by specifying a reasonable mass profile that without predetermining it using PV inversion, but it's a bit of technicality. It still works quite well. Now we'll see later. And also it requires PV on isentropic levels, and many climate models do not have this quantity, which can be a bit of a problem. But on the advantages, it's fast to run, and it results in a background flow that retains zonal variations. Let's go to the case studies then. In June 2022, it was not maybe the strongest heat wave ever recorded, but there were several heat waves occurring at the same time over North America and Europe. I highlighted here in blue the heat wave occurrence. It's the heat wave mask in blue is being provided by Emanuele Russo. It's based on the work with Daniela Domaisen. Essentially, you have to see it as somehow a decent heat wave threshold. So temperature should be 2-meter temperature should be larger than the 90th percentile, and this anomaly should persist for at least 3 days. And we can see the heat wave over North America here, a little small one here on the southern tip of Greenland, then a bigger one over Western Europe, and another one over the Middle East. And you see they are both connected, it seems, by a nice wave train series of troughs and ridges. It spans the North Atlantic. But are these heat waves really dynamically connected? Are they part of the same wave packets? Is there a waveguide that connects them? Let's try to apply the waveguide diagnostic that we just discussed now. And here we will see now a little animation with 2 different plots. Here on top, there is the gradient, the PV gradient of the zonalized state obtained by this random zonalization approach. And below, there is this depth of the waveguide, meaning like how deep the waveguide is, the criterion somehow for how many isentropic levels the criterion is satisfied. And with the stars, we have the heat wave mask again, while we see, on the other hand, the meridional wind in red and black. So if we go forward in time, we can see how the waveguide evolves. So let me see, I can go back and forward in time. The time I selected before was this one here. We have the 3 waves and all the wave train that propagates. And at this time, more or less, we also have an area of strong PV gradients, you see in the upper plot, that goes all around the globe. And this was not the case before at the beginning. It was a bit weaker. And it will not be the case at the end. We will see it again. And maybe this the presence of this waveguide corresponds to the stretching of this wave, of all these waves from the North Atlantic towards the Middle East. And we can see also the heatwaves associated with them. And you see, more, if we go back and forth, you see that the waves more or less follow this green contour in the plot below. This. And one thing I also like that is it tells me, oh, this really behaves like a waveguide. Take a look at this trough here over the east coast. It's quite elongated. It stretches meridionally from Canada to Florida, but only the northern part is in the waveguide. What we expect is that the upper part in the waveguide will propagate eastward, while the part that is outside of the waveguide will stay there and lag. And at a certain point, it will break, and we have a cutoff formation. I find it very nice because it looks like this place on the upper part of the trough is like favored. It really looks like a waveguide. And we can also visualize all these animation as a Muller plot. And here we see, again, it's the same colors of before. So the gradient of PV is with the blue, the green, etc. With the stars, we have the waveguide, and with the wind, it's the usual wind somehow that we have here. We can see the 2 heat waves. The one over North America seems to be part of this Rossby wave packet that we see here, while the one over Europe actually seems a bit unrelated to a wave packet. It was there even in an area of low wave guidability, in a periods with low wave guidability, and it continues until this second wave packet arrives. We can also see that not only the propagation of the waves, but even the propagation of the waveguide itself. This waveguide is sometimes stronger, sometimes weaker, and when it is strong, we also see, in the sense of colors, we also see some strong waves in terms of contours. And also when the PV gradient is weak, we also see less waves, as I tried to highlight here in these 2 regions, to the right part and to the top part of the Muller diagram. And also, if we use the zonal wind as a diagnostic, so comparison with the plot to the right, we see the zonal wind is more spotty, sometimes has some lags in there. For the sake of time, I also move to the last example, which is the 2010 Russian heat wave, very famous. Probably many of you have researched on that. And what we see here is this very nice, large and persistent blocking of Western Europe, and the waveguide that divides in 2, it seems, one over starting from the upper part of the block and one starting from the southern part of the block. How is our diagnostic performing? And this is the plot that I really like a lot. This is an average of waveguide frequency in the period of the peak of the heat wave between the 23rd of July and the 9th of August. It's an average of the daily waveguide frequency. And we see we have a very strong waveguide over the North Atlantic, right, straight elongated from California to the UK. And then it quickly interrupts as the blocking is there. The center of the blocking has completely no waveguide recorded in this period. And then we see the upper portion and the lower portion of the waveguide, a split somehow. And maybe one can wonder if this is an optimal configuration to have a very strong blocking that is maintained for a while by the continuous influx of eddies coming from the waveguide to the west. And this can explain the exceptional persistence of this and intensity of this event. And yeah, in this diagnostic thing shows it in a very neat way. Maybe this is like why this was a special event. For the sake of time, I say, if you're interested, consider submitting an abstract to the Rossby waves and jet dynamics. And then I go from the summary, which I can summarize again quickly. This waveguide diagnostics, which is based on close normalization, seems to behave like we expect a waveguide to do. And I find this very exciting, and I wanted to share this with you today. Thank you very much. Yeah.
Should I go there?
You can try from there. Maybe they can hear.
Okay, maybe I come here
Yeah.
and it's a bit closer to the microphone. Yeah, thank you very much. It's always a pleasure to listen to your talks.
Thanks, Wayne.
I have a question related to these two cases you mentioned at the beginning, that there is a difference between something which is like an atmospheric pattern, which is super persistent, and then these patterns which look like persistent, especially if you consider averages, time averages, but they are actually transient and they are always kind of recreated, right? Recurrent.
Yeah.
So my question is if there is at all a case in the atmosphere when we have this perfect persistence, because I mean the atmospheric dynamics is chaotic, and also in case of long-lasting blockings, you can see that they are recreated or strengthened. So I have the feeling that it is never like something. It's never like perfectly persistent. And then also, but it's also not transient. I wouldn't call it transient because if you look at the local anomaly at a certain place in time, like also on the Hoffman plots, you see that this positive geopotential height anomaly is recreated again and again. So it is in a way persistent. Yeah. So it's, I don't know. It seems, for me, it seems to be like something between.
Thanks, Melinda. I really like this comment, and you raise a point that is indeed very. It's true. We see, for instance, the blocking that recreate themselves, and by doing that, for instance, sometimes they propagate westward. There is a case for the Scandinavian blocking becoming random blocking. As you, maybe I don't have an answer to your question. It's quite provocative, but your comment is. Yeah, I agree. It's very difficult to put. It's something to think about. Maybe it's posing the right questions. Like, it depends on the phenomenon we want to find, and it's not always possible to have a clear-cut distinction. Maybe one thing that I can add is that the concept of waveguide itself relies on the scale separation. That there is somehow something that persists on a longer time scale than the waves themselves somehow, and so it's possible, maybe in some cases, to find at least a minimum scale separation, but then maybe this waveguide is also part of a larger wave, and then this wave also propagates slowly, as it can maybe this example here was showing, and so yeah, thanks Melina, anyway, for the question, for the comment.
Yeah, also thanks for the talk. I guess maybe more theoretically, we create these quantities because they satisfy a certain properties, right? So I understand PV inversion is not easy, but the reason that we do it is because it's connected to a conserved quantity. So I guess the provocative question is, if you don't conserve PV, then what do you have anymore? And how do we usefully interpret it? When you're taking a 60-degree longitudinal window, and this is not your work, it's the waveguide. So I guess for me, it's more about the end product and how useful it is to interpret. The analogy I would draw is to the Hadley cell. It's a theoretical concept based on angular momentum conservation. When we look at circulation, it doesn't look like a Hadley cell, as it's only symmetric and angular momentum. So I guess maybe that's a parallel to think about. But ultimately, with the waveguide ability, I guess, for this workshop, what does it get you for the heat waves? There's a waveguide all the time.
There's a
waveguide pretty much all the time, right?
Although it changes, since it's not always.
Maybe not in the same place.
It's not always. It doesn't not always having the same strength. You can see it like from the.
Right. I guess the key question is, what does it tell you about the heat constraints?
No, that's also actually a great comment, like the one in the sense that it forces us to think. The PV conservation is in each 60-degree window, the PV is is so it's conserved. It's maybe not in the the prevention is not always the case. Yeah, that's a bigger problem. It looks like it behaves like a waveguide. And I was happy to see that, and I really wanted to share that. But probably some more work is needed to make sure that the conservation can happen also in smaller zonal windows. Thanks.
Yeah, really cool work on sympathy of this approach. Quite nice. My question would go into a similar direction, like what degree is the background state that comes out of that zonalization actually comparable to other approaches, like just taking a zone mean picture of some seasonal mean or like some, I don't know, weekly, bi-weekly average or so. I remember the first paper from 2021 by Bert and Paulsen there. I felt that the zonalized background state really has not much in common anymore with the circulation pattern as it was observed there. So the zonal wind that came out of the zonalization process was like really fast, like more than 50 meters per second or so, and that really changed the stationary wave number that was supposedly active during the time. So my question would go into that direction, if that is still the same approach, and if this waveguide does allow any type of inference regarding the ruling wave numbers that might be active, like the spectrum, also that might be favored by certain types of waveguide strengths, because that would allow some predictability, right? And it would also resolve that physical reasoning issue that you also that would be my question. Like, is it a reasonable background set in terms of
no, that's also actually a great point. Maybe indeed, if one can stratify with respect to the state of the background flow and see how the waves are behaving according to some categories of background flow. I think the objective was to obtain a state that was as much as possible wave free, and indeed it's uncomparable in some aspects to the. But in the example here, we see that the waves more or less follow this contour here. So it seems somehow useful as an approximation of the waveguide. And even you see the upper part of the lower part of the waves, it's something that they find quite striking. And also the propagation, you can also see when we have this moment, we have the connection between the two waveguides. We see that we have actually wave propagation, from the North Atlantic to the subtropical jet. So in theory, I share your concern. Looking at the data, looking at it, I feel a bit, on the other hand, a bit more hopeful that this is useful. But yeah, as Tiffany was said, we need to get an even stronger somehow theoretical basis to be sure that what is happening is reasonable, or at least not conserve the PV, but in a way that it is reasonable enough to neglect or something like that. Yeah.
Okay, so we already accumulated 15 minutes of delay.
So
I would, but this was a great start for our discussion. But remember that we always have at least half hour for further discussion at the end of the day. So thank you so much, Jacopo. And so we now have 2 talks online. And our next speaker is Iago Perez from the University of Oxford, talking to us about wave-breaking events and their link to Rossby wave packets and atmospheric blocking. And now we're looking at Southern Hemisphere.
Okay, let me share the screen.
Yeah.
Okay.
And we'll give you a warning 1 minute before the 12 minutes.
Okay, can you see my screen?
We can.
Okay. Well, first of all, I would like to thank people from the workshop for letting me have this talk. This has been done. This research has been done with the collaboration of the Universidad de la República in Uruguay and from the people from the Institute of Interdisciplinary Physics and Computer Systems. And without further ado, let's begin. So first of all, we'll do a quick introduction about the field. So we know that Rossby packets are meanders or deviations of the jet stream that are considered precursors of extreme weather events, that they normally last between 3 to 6 days in the atmosphere, but in certain conditions they can stay up to 2-3 weeks before disappearing. Sometimes when these packets propagate, as we can see in the row figure, they start gaining amplitude until they break in the atmosphere, and this causes a wave breaking event. And during this event, the usual wind and energy flow is interrupted, and as a result, this changes local weather conditions. Nonetheless, one interesting fact is that when these wave breaking events are big and stable enough, they can behave as atmospheric blockings, which cause the development of extreme weather events such as heat waves or cold spells, of course, if they last long enough in the atmosphere. So previously I stated that Rossby packets can break, and this breaking could behave as a blocking and end up in an extreme weather event. Nonetheless, nowadays it is still not known when these packets break and are able to cause blocking events. So the main question that we want to answer in this presentation is it possible that it would be possible to link wave breaking events produced by transient packets to atmospheric blocking development? Answering this question will enable us to improve the the detection of extreme weather events between 10 to 30 days in advance. Nonetheless, in order to address this issue, we need to respond another two sets of questions, which is when a transient Rossby packets can manifest a wave breaking event, and when these wave breaking events can can be sufficiently extensive and persistent that can trigger atmospheric blocking development. So in this study, we use dataset from the ERA5 analysis with 2.5 degrees of spatial resolution and daily time step from December to March, which is the period of the austral summer in the Southern Hemisphere, and from 1979 to 2020. About the variables used, we selected meridional zonal wind speed as well as temperature from several layers in the atmosphere, as well as geopotential height at 500 hectopascals. The framework of the work was as it follows. First, we track transient Rossby packets and we classify them into long-lived and short-lived packets, which will be defined in the next slide. Then we identify wave breaking events that occurred after a Rossby packet stopped propagating. Third, we search for atmospheric blockings with different strength and intensity. Fourth, we characterize the wave breaking events that are linked to the short and long-lived packets that were propagated in the atmosphere. And lastly, we search for wave breaking events that manifest their near blockings and assess their link with the Rossby packets. So I'm going to describe how did we search for Rossby packets in the first place. In order to do so, we start from meridional wind speed data at 300 hectopascals, and we transform it into wind envelope, which is a variable that quantifies the strength and intensity of a packet. So in this composite map, we show the wind envelope for a specific day after filtering low intensity noise, and areas where the wind envelope is the highest indicates the location, the center of a Rossby packet. Then we measure the mean envelope between the mid-latitudes. This is between 40 and 65 degrees south. So we can have a homology diagram of the temporal evolution of the wind envelope during their propagation. Afterwards, we applied a Rossby packet tracking algorithm, which is able to locate the center of a wave packet and follow its propagation to the east. In the right figure, the gray and black points show the performance of the algorithm while following the trajectory of a long-lived Rossby packet. It is important to highlight that this algorithm will only search for transient Rossby packets or Rossby packets that travel with speeds from 15 to 45 degrees per day, and we tested the performance of the algorithm with other studies. Then we measure the characteristics of this packet, such as the dissipation areas, or where they disappear, and the lifespan. And then we classify them into long-lived packets when these packets last more than 8 days, or in short-lived packets when they last between 3 to 8 days. So now that I explained how do we search for Rossby packets, I have to explain how do we search for wave breaking events. In order to do so, we computed a second tracking algorithm which is able to detect the regions where the potential vorticity field overturns, because these signals where breaking events occur. And then we search for wave breaking events that manifested after a Rossby packet stopped propagating. So in the down figure, we are showing the black dashed line indicates the area where the Rossby packet was last seen in the atmosphere. Meanwhile, the red square shows an area where the potential vorticity field overturns and signals the location of a wave breaking event. Nonetheless, we apply a specific set of criteria. First, wave breaking events must have a zonal extension above 15 degrees or being like large-scale wave breaking events. This was in order to have wave breaking events that have the spatial scale similar to blocking. And then these wave breaking events have to manifest 2,000 kilometers from the area where the Rossby packet stopped propagating. When these two conditions are met, the tracking algorithm will be able to follow the propagation of the wave breaking event until it disappears from the atmosphere, and we measure the characteristics such as the day it appears, the longitudinal and latitudinal extension, its shear, and the lifespan. Lastly, we need to show how do we search for atmospheric blocking events. In order to do so, we applied a third tracking algorithm based on Tibaldi and Molteni 19 and retained blocks with different intensities and lifespans. Then what we in the So in this slide, we are showing the geopotential gradient at 100 hectopascals, and the black line signals the manifestation of a blocking event in the atmosphere. And then what we did is apply the second tracking algorithm to search for wave breaking events that occur nearby where the blocking took place, as we can see in these white figures. Again, we used this distance of 2,000 kilometers to search for blocking events that might be preceded by a wave breaking event. Lastly, what we did is measure the proportion of this wave breaking activity that could be linked to the Rossby packets that propagate in the atmosphere. And now I'm going to show the results obtained. What we found is that around 40% of the times, both short-lived and long-lived packets show large-scale wave breaking events after their propagation. Nonetheless, as we can see in the lower figure, where we're showing how long they last, the wave breaking events associated to long-lived in the left figure, and to the right with short-lived, we see that wave breaking events linked to these Rossby packets only last for 1-2 days. And why is this important? Well, atmospheric blockings need to last for several days or even weeks. And because the wave breaking events only last for a couple of days, at first glance, it seems that wave breaking events do not seem linked to transient Rossby waves, do not last enough time to be considered as blocking events. But where the wave breaking events occur in the first place? Well, in the lower left figure, we're showing the areas where the long-lived and short-lived packets tend to break. And we can see that long-lived packets tend to break between 180 degrees and 300 degrees, which is the total of the Pacific Basin. Meanwhile, short-lived packets tend to break a little more to the west. And this we find that this is important because even if the wave breaking events do not last enough time to be considered as blocking, they can be considered as precursors of weather regime transitions. And what this is telling us is that long-lived Rossby packets might be precursors of weather regime transitions in the mid-latitudes of South America. Now, in the last part, we're going to link between Rossby packets, wave breaking, and atmospheric blocking. So when we we found that 105 times an atmospheric blocking event occurs in the atmosphere, it is preceded by a large-scale wave breaking event. Nonetheless, barely any wave. We didn't find any wave breaking, almost no wave breaking activity that could be associated to transient Rossby packets. Thus, one of the main findings in these works is that propagating Rossby packets do not seem to be directly linked to atmospheric blocking events, at least by wave breaking mechanism. They might be related by other dynamical processes. Also, it's important to highlight that in this study, we only focused on transient Rossby packets. Those are the packets that travel between 15 to 45 degrees per day. Thus, another possibility is that slow-moving Ross waves might influence the blocking development by wave-breaking mechanisms. And now, summarizing what we see in this presentation, here we characterize wave-breaking activity associated to transient Rossby waves and whether this wave-breaking activity could be associated to atmospheric blocking development. We found that wave-breaking activity associated to transient Rossby waves do not seem to be directly linked to atmospheric blocking development, but we found that transient long-lived Rossby waves might be precursors of weather region transitions in the mid-latitudes of South America. The results are under review in the Journal of Geophysical Research, and if you have any questions, I will be more than happy to answer. Thank you for your time.
Thank you so much, Iago. Are there questions? Any question from the audience? Any question online?
Yeah, actually, yes. There's one request by Maria Pirina, I think.
Yes, hello.
Yeah, hi.
Can you hear me?
Yes, yes, we can.
Okay. Thanks, Iago. It was a very interesting talk. I was wondering if you did the same analysis, not regarding blocks, but ridges.
No, because here we just wanted to assess between the wave breaking and between wave breaking and blocks, but not in ridges. But it's a good question for future research.
Thank you. Yeah.
Other questions? If not, let's move on. Thank you so much, Iago, with our next speaker, in fact, the last before the coffee break, Marco Cadau from USPADIA, talking about the relationship between atmospheric blocking and Arctic mid-latitude thermal gradient. Sorry, Marco, you cannot be here in presence. We cannot hear you.
No, we cannot hear you.
We cannot hear you.
Can you check the settings of your mic?
I'm just gonna try to log in again.
No, still muted. Maybe you can take off the headphones. Sometimes this is.
Now?
Yes.
Yes.
Oh, awesome. I'm so sorry. Okay, can you also see my screen, right?
No, we see a blank screen.
No, you don't. This is weird. I tried sharing again, sorry.
Yeah.
Now?
Nothing.
Nothing is happening.
Oh gosh. I can't tell why it's not. sorry, just 1 minute more.
Mark?
Now?
Oh, yes, now we can
okay,
see.
great.
Oh, awesome. Sorry for these problems. And I'm so sorry either to be there, Simona. Unlucky COVID. So, good afternoon, everyone. First of all, I'm Marco, third-year PhD student in USP Pavia. And today, I would like to talk to you about a little more in detail about the relationship between atmospheric blocking and Arctic mid-latitude thermal gradient, as Simona mentioned. Thank you, Simona. So, to quickly introduce the topic, let's say that, as you probably know, Euro blocking is pretty relevant and it has a pretty much studied association with Arctic warming, and especially, in fact, in the Euro region. Usually, the whole blocking, in which in the plot you can see acclimatology in winter, is pretty relevant for large-scale climate dynamics in winter. But in the Euro blocking is particularly important because it might inhibit sea ice formation and maintenance over the Arctic region in general, and especially over the Barents-Kara seas, which leads to further Arctic warming. So we could say, literature says, we have a linkage, at least, between Euro blocking development and activity over sea ice development, and then to Arctic warming. So this is more or less what recent studies say to us. So I wanted to introduce another index based on the Arctic mid-latitude thermal gradient. As you can see, I'm talking about the first one in the left, so the red one. I based it on the 1000 hectopascal temperature anomalies between Arctic and mid-latitude. So roughly the anomalies in 1000 hectopascal temperatures in the Arctic minus the anomalies in temperature in mid-latitudes. We can see, always in the red plot, we can see that, we can perceive a trend because we see that this AMG index is increasing in the last decades. And this is also an expression, of course, of Arctic amplification. In fact, this index is pretty much utilized in literature to have an expression and a definition of Arctic amplification. And is also leading to basically a weakening of the Arctic mid-latitude gradient. I wanted also to isolate, let's say, the high frequencies of this time series that you see in the right plot. Can you see my pointer from the room?
Yes.
Well, yes, we can see.
Okay, thank you. So in the blue plot, we see just the high frequency component of this time series. In a few slides, you will understand why I decided to extract, to retrieve this, let's call it internal variability of this time series. In fact, I wanted to correlate the blocking frequency grid point for each grid point with the Arctic mid-latitude thermal gradient time series you have seen. These have been made for winter, so for the JF, so December, January, February, from 1940 to 2023, so a pretty long time series, I would say, from ERA 5 data set. And from these plots, we can see that there's a clear connection, at least, between blocking frequency over the Ural region and the Siberian region and the Arctic mid-latitude thermal gradient. But we see that the signal is more relevant, is stronger over the B time series, so in the correlation with the blue time series here rather than the red. So this means that the internal variability of this time series might be more associated to Ural blocking impacts and association with Arctic dynamics, let's say. So a part of the variability between this relationship might be explained by Ural blocking internal variability. So going through my research questions, basically I wanted to wonder what are the main climate drivers in mid-high latitudes when the variability is not explained by this relationship. So why in some years, in some months, Ural blocking is not relevant to determine the Arctic mid-latitude gradient? What are the main climate drivers under these circumstances? And how circulation patterns are characterized under these circumstances? So I plan to classify, let's say, all the months in the time series. So I repeat it again, from 1940 to 2023, December, January, February. So this should be 249 months that I want to classify according to their values of the AMG-HF index. HF stands for high frequency, so the internal variability part, and their value in frequency of instantaneous Ural blocking. And we can define many areas in which in this scatter plot, but the more relevant that I wanted to focus more are the red and the purple, which are the, let's say, climatological, because they're based on what we should expect. So strong AMG-HF index means a lower gradient, so lower gradient, high Ural blocking frequency, vice versa, low Ural blocking frequency, strong gradient, we can say. So these are supposed to be normal, allow me to say this, and these are not normal circumstances, so the non-linear parts of the variability between these two large-scale dynamics, let's say. So higher AMG-HF index, so a lower gradient between Arctic and mid-latitudes, but also weak Ural blocking frequency, and here vice versa, strong Ural blocking frequency, strong gradient between Arctic and mid-latitudes. And in fact, as we might expect, these two areas, the blue and the pink one, are the least populated with respect to the red and the purple one. So I want to analyze the climatologicals first, and we can see that we perceive the special pattern of gradient in temperature for sure in both circumstances. I mean, here the gradient, the thermal gradient was supposed to be lower, sorry. In fact, it is. We see an Arctic warmer than average, and mid-latitudes, especially in the Eurasian continent, mid-latitudes are significantly colder than average. In contours, in the magenta contours, you see significant values. And in the other normal case, so when Ural blocking is weak, Arctic mid-latitude gradient is strong. In fact, the Arctic Ocean is warmer than average, colder than average, and the mid-latitudes are warmer, basically. In fact, we observe also a strong positive anomaly on SS, so in the purple points. We see a strong positive anomalies of blocking frequency over Urals and Siberia, and a negative one instead in the other pattern. So something we could expect, because it's something we expect from literature and from studies. In contours, in the left plots, we can see the geopotential anomalies. So the clear is not so zoomed, but yeah, in the clear contours, it means a positive geopotential anomaly, while the dark one, negative one. And these are the non-linear patterns I was mentioning earlier. Like we still observe a weak Ural blocking intensity in SW in this pattern, which is the blue points. Okay, these are blue and pink points. Okay, in the blue points, we see a negative blocking anomaly over Urals, which is fine, but still we observe also this might suggest a positive anomaly northward, so maybe a blocking displacement, because we don't observe blocking over Urals, but we observe it in non-conventional areas like Barents-Kara Seas and higher Siberia. Also, geopotential anomalies might support this hypothesis. This is still an hypothesis, indeed. While in WS, so in the pink points, so when Ural blocking frequency is high and the gradient between Arctic and mid-latitude thermal gradient at 1000 hectopascal is strong, we see that, yes, Arctic region is warmer than average, but the positive temperature anomalies are not focused on the mid-latitudes anymore. They are more focused in a complex and an hemispheric signal, an hemispheric pattern, because we see positive anomalies. You can clearly see positive anomalies over Africa, Arabian Peninsula, Eastern, sorry, Southeastern Asia, so something much more hemispheric, I would say. And more importantly, we can see that there is still a positive anomaly over in blocking frequency over Urals, which is fine and which it was expected too. But we see also positive anomalies in blocking frequency over all other regions in the Northern Hemisphere. So in Greenland and in the Bering Strait area, which are also maximum in blocking frequency, climatologically speaking, let's say. So the blocking presence here, the more likely blocking presence here, might inhibit the heat and moisture transport from the mid-latitudes in the oceans to Arctic. That's why we could expect a Arctic colder than average. And this in the right plots, we see meridional wind at 850 hectopascal. We see that the anomalies are negative. So there are no advections here and here, thanks to the blocking frequency in anomalous regions, in unusual regions when blocking is strong, also in the Urals. So this might suggest a co-occurrence of blocking in many areas. So definitely a Rossby wave pattern that I would like to investigate more, let's say. And this is something that shows that advections in this case, even though your blocking imprinting is strong over Urals, advections are inhibited or obstaculated, let's say, but other presence of other blocking regions in the same moment, or maybe with a lead day in different areas, I would say. So I just leave the conclusions here because I think I'm a little out of time, and I thank you everyone for the attention.
Questions for Marco? Online? No. Okay, there is two here, so Jacopo maybe, and then.
Thanks, Marco. I was wondering if you have checked the presence of like your Euro blocking in the different configurations, if it is related to a wave train or not. So if it's like if there is like, I don't know, some
Yeah, it was,
activity flux anomaly that goes through the blocking in some circumstances or not. Because then if you have a transient wave train, sorry, if you have a more transient wave train, then we can see the impacts over different regions of the hemisphere, while if it's more blocking, it's more closer to the impact region.
I'm not sure I understood all the words of your question.
Is blocking or is it part of a wave? Have you checked if there is with some diagnostics of waves, like wave train diagnostic? Do you think maybe the answer can differ according to the subset that?
I completely agree with you. I mean, it was definitely a next step of the analysis that I wanted to pursue, because I want to, me too, to check out the Rossby pattern in that case, in those months. Also because, let me show again. Just show the screen quickly. Okay, yeah. The months in the pink areas are also not so much. So I think it's easy to check similarly every month to check, yeah, the Rossby wave pattern and the guidelines, as you were showing earlier, to understand whether how the Rossby wave pattern is influencing the blocking frequency we see at the troposphere, let's say. There was also another thing I want to add is, no, okay, I think did I answer to your question?
Yes, it was more a comment. Maybe it can be helpful for further analysis.
Yeah, no, I definitely, especially because yeah, also not so many, and I also was suspecting, I don't know what if you agree or not, that maybe blocking events might be also not occurring in the exact same days, maybe with a day, 2, 3 days in difference, maybe.
Yeah, you're considering the daily data or monthly data?
No, these are monthly.
Monthly, yeah, then yeah, it would be great to check even the.
So yeah, basically I cannot. Yeah, I cannot tell you with in exact days which days were involved in blocking events. Also because I don't have a filtering between blocking days. I mean, I'm not defining blocking events according to how many days they last. So it's just raw blocking frequency on those months. So that's why.
One of the issues, sorry, this time averaging in that a certain causality becomes complicated. But yeah, thank you for the yeah.
Thank you.
There was another question?
Yeah, hello, thanks a lot for your talk. I was wondering whether maybe.
Can you go a little closer to the mic, please? Sorry, Joseph.
Yeah, hello. Thanks a lot for your nice talk. I might have missed it, but are you limiting your analysis to a certain month or not? And whether you would think that some months are more, or some seasons are more interesting than others, in particular for the further effect of the blocking as a precursor for stratospheric warmings in winter, or yeah, you know. Also the sea ice variability, I'm sure, is different depending on the season.
Valerio, Simona, can you repeat the question because I didn't understand really well. Sorry, because I didn't have the earphones on.
Yeah, did you limit yourself to one season, or was it a year-round analysis?
Ah, yeah, okay. No. For now, you know, that's a really good point because for now I'm just looking at winter, as you see. At the beginning of my PhD, I was looking to summer as well. At a certain point, we just decided to focus on winter only, but I was really definitely into looking at other seasons also to understand differences, other blocking patterns, you know, weather regimes in other seasons are completely different. So yes, I would like definitely to repeat it for other seasons as well, especially summers also.
Thank you.
Okay, I think there was a question online.
Hi. Thank you for the talk. So in the beginning, you have shown that the AMT Arctic, kind of related to the frequency of the blocking. So those two are related. And then you use those two as the coordinates to divide them into different groups. But to me, I feel like if you wanted to use two variables as x and y axis, let's say, somehow they should not be related. If they are related, then why it can be used as kind of two dimensions?
Let me share the screen again. You know, at least something that I thought about is like the relationship between these two. I mean, considering that, the correlation values. I mean, it seems that there's a relationship indeed, but if it was the correlation values were really high, I expect to see the values in this straight line, right? In fact, we don't see this. We see something in which there is an association, I would say, because we see that in fact in the red and in the purple regions there are more points, but still there is no linearity in this relationship. Indeed, I don't want to assume this relationship is quite linear, like 100% linear. Definitely, I will say that. I understand your point still, but yeah, I don't think it's completely linear. So I was like maybe allowed to plot these points even though they were not completely independent, maybe. Did I answer to your question, maybe?
Yeah, that's great. Thanks.
Okay, thank you.
Okay, so let's give a round of applause to all of the speakers. And so we have a coffee break. We are running a little bit late. So my suggestion would be, so that we don't get really delayed, to maybe try to keep it within 22 minutes and be back at 4:30. And there is some refreshments as you walk out on your left. And the speakers, Valerio, you have Paolo.
Yes,
Did you-
I will upload my.
Great, perfect.
My
Okay, so let's.
Ora si registrerà la conferenza.
That was just the message that talks will be recorded. And so it is our pleasure to introduce Angelica Zagar from the University of Hamburg. And she's going to be talking about trends in the global atmospheric circulation in wave number space. And Angelica, so if you can keep it to 25 minutes, and we'll give you a 2-minute warning. Thank you.
Thank you very much. And I really wish I would be in Bologna instead of online, but I have earlier agreed commitments. And so I thank you very much, Valerio and Simona, for the opportunity to present some of the research in my group online. So in this talk, I will discuss some circulation trends, focusing on the tropics, and how we have been attempting to understand them using wave number filtering. So let's start. First, I would like to show you a few plots from the recent, last year actually, paper by Adrian Simons, in which he analyzed trends in ERA 5 reanalysis between 79 and 2022. So we are looking at 200 hectopascal level, mean state zonal wind on the left in meter per second, and then two other plots.
Sorry, we cannot see your slides scrolling.
Oh, okay. So I'm not sure why.
Yeah, maybe you can try to unshare the screen and then
Okay.
share the screen as what is named full screen should be. There are three options, the one on the right.
All right. So is it this one?
Yes, or I mean, then you can jump to use slideshow, and then we don't see your comments.
It's not working, right?
Maybe if you see in the top left, you can stop the screen.
So started.
All right, now it's fine, at least for us.
Okay, is it still fine?
Yes.
Yes.
Okay, so sorry for that. Okay, so yeah, so let's look at this figure on the right. In this figure, he kept only statistically significant part of the zonal wind trend, and then this gray edge, this gray colored edge that you see, this is the change which we get if one reduces confidence level to 90%. So we are looking at this large area of the tropics extending from the maritime continent towards South America with negative trends, on average little over half meter per second of the enhancement of tropical easterlies per decade. Okay. And this is what we would like to understand, these tropical trends in circulation. So the big question I would like to address is about modes of global variability that are associated with these observed circulation trends in the tropics. So, and how to address this question. To do this, I would like briefly to, now I can't go next slide. Okay, so I would like to simply remind ourselves that usually we discuss modes of variability in terms of indices, and those that are based on directly on observations, they are surface indices and few. But if we want to analyze circulations, we normally have to use reanalysis data. And then depending on the definition of the index, depending on the level of reanalysis data set, one can get actually different, even opposite trends. And here is an example from the paper by Matis Pikovnik et al. Last year. You are looking at the Northern Hemisphere headley cell, Southern Hemisphere headley cell, and the total headley cell in era 5 and era interim. And then the top 4 plots are showing trends depending on the stream function indices, depending on the level chosen to define the index. And the bottom 2 panels are headley cell index based on the geopotential or vertical velocity, or actually one global that I proposed. So, but the main message of this plot is that the trends in amplitude and even sign can vary. So the argument, what we would like to do, we would like to have a global index. And then because trends in circulation and trends in thermodynamics are coupled, we would like index that is multivariate, that represents both thermodynamics and circulation. And then, of course, this is difficult because it should represent both divergent and vorticity-dominated circulation, both tropics and the extratropics. And for the extratropics, we have a well-defined understanding of large-scale circulation, quasi-geostrophic theory, while for the tropics, much of our understanding is based on the linear wave theory or Matsuno-Gill picture and these linear large-scale equatorial waves. Some of them are presented in these either rotating or resting spheres. But I'm showing in the top plot, I'm showing this now very well known analysis of the OLR data by Matthew Wheeler and George Kiladis almost 25 years ago. So what you see on the left is a background spectrum, and then symmetric and asymmetric part of the deviations from the background. And then these deviations are then fit with the dispersion curves for the linear equatorial waves. And these results have largely motivated understanding of these large-scale tropical variability in terms of these large-scale waves in the tropics. So, what we would like then, we would like to see how these trends in tropical circulations are coupled with the variability associated with these waves. And we would like, of course, to have this done in the wave number space to associate variability with different scales. But we also don't want to use frequency filtering because of its assumption of linearity in time and its removal of trends. So we have to aim at wave number filtering. And with this, I would like to discuss briefly, I would like to spend some time discussing different ways to do wave number filtering of circulation. The first one, which I think we will see more during the workshop, is one-dimensional FFT. It is done along latitude circles. It provides a single variable at a single level analysis in terms of the zonal wave number. So it's a univariate analysis that can be applied to any gridded data. It's very well suited for the middle latitude, where we can assume that the large scale flow is the vorticity dominated, so that the scales we are analyzing by this wave number filtering are made of Rossby waves. Okay. So, but then of course, taking this to the tropics will not really help me in understanding my equatorial wave contributions, because I have a mixture of the Rossby waves, of these other equatorial waves, Kelvin, mixed Rossby gravity, even the large scale inertia gravity waves. Okay, so another very widely standard use wave number filtering technique is that of spherical harmonics that we know now almost over 50 years, and we have some major global NWP systems built using spherical harmonics. It is global. It represents data. We can see them either as a function of the zonal or global wave numbers. It is also a univariate representation, so operates variable by variable, level by level. It is normally applied to discuss synoptic and inertial range part of the spectra. It is very well suited to discuss kinetic energy spectrum, and it's often used to see to what extent models fit the Nernstrom gauge spectrum. And because the spectrum is made as a sum of the rotational and non-divergent part. So, and then of course, spherical harmonics are familiar because they are eigensolution of the barotropic vorticity equation. So this is a perfect representation for the vorticity in barotropic fluids. Okay, so here is the example of the representation using spherical harmonics. So this is in average over 1 week or R5 data at a single level. So, and this is ECMWF data, so it's a triangular truncation. On x-axis, you see the zonal wave number, on y-axis, the global wave number, and this is energy, joule per kilograms. And then this total energy, which is figure on the left, is a sum of the rotational and divergent components. And what I would like to point out here that what these spectra illustrate, they illustrate anisotropic nature of the spherical circulation. So if we look somewhere at wave number 20, we see that the energy is independent of the zonal wave number for a single global wave number. But then if we look at the planetary scale here, just at the bottom of this triangle, we see actually that so there is a substantial part of divergent circulation in the flow, and this is where the tropical circulation comes in. So my point is that the spherical harmonics are less informative in the tropics because of these special tropical equatorial waves being made of both vorticity and divergence. And now just a comment, now we can represent the global spectra either by integrating along the zonal or the global wave number. And then this is what is shown in these bottom two plots. So you see on the left, the global wave number representation, on the right, zonal wave number, and the spectra are almost identical from synoptics and the smaller scales. But if you look at planetary scales, you see that they are quite different. So again, this is related to the formulation of the spherical harmonics. And again, so you see that, of course, globally, the large scale circulation is vorticity dominated, but in this vorticity at large scales, there is a part of the tropical circulation. For example, the planetary scale Kelvin wave is almost half-half. It's 50% made by the vorticity, 50% by the divergence. And this brings me to the third approach to the wave number filtering, which is one we exercise in my group, and just a few others group are using it. It is one based on half harmonics. Half harmonics are eigensolutions of the global primitive equations, and this gives them physical meaning. Like spherical harmonics, they are global, but they operate on 3D data. This makes them a bit more complicated, or they take more data as input because they involve both vertical and horizontal decomposition. But the important difference is that this is multivariate. So we get regime decomposition. And then this decomposition then involves Rossby waves, and then these motions of the first kind, as it was traditionally called, which are inertia gravity modes, involving then also Kelvin modes and mixed Rossby gravity modes, and all inertia gravity modes. And I tend to refer, since a couple of years ago, and this was actually the suggestion by Ted Shepard, to call these three types of waves together: Kelvin, mixed Rossby gravity, and inertia gravity non-Rossby modes. Okay, so as I said, this kind of decomposition is a two-step process. First, we perform vertical projection. And here are just example for some reanalysis, error reanalysis data we use. So we have these numerically computed structure functions that are used to decouple data vertically. And this simply means that we represent baroclinic atmosphere in terms of n different shallow water systems. And then half harmonics are eigensolutions of these spherical shallow water systems. So then we perform wave number filtering on these very many or number of shallow water systems. Each of them has different vertical depth, and these vertical depths are eigensolutions of the associated with these vertical eigenstructures presented here. So this is now, I've been running now for exactly 10 years, that the web page that is analyzing in this way deterministic analysis and forecast of the ECMWF system. So here I would like to show the difference between half harmonics and spherical harmonics. So the plots on the top, they are those you have seen earlier. So the red spectra are the vorticity spectra. And then in the extratropics, we normally use the blue spectra, which are divergent energy spectra. We use them as proxies for inertia gravity waves, which is just perfect for the small scales. But as I discussed earlier, for the large scales, it is really where the tropical influence come into both rotational and divergent spectra. It is the discussion is more complex. And this is where these two spectra at the bottom are more informative. So now I have the difference is that now on the top, in the top spectra, I had kinetic energy. In the bottom spectra, because I have multivariate representation, I have mechanical energy, so both kinetic and available potential energy. And now the total energy, which is the black line, is a sum of the Rossby mode energy, which is vorticity, plus little divergence due to geostrophic due to beta effect, and then the red spectra, that is all non-Rossby modes. So you see they are similar. I mean, they both have crossing, but the important difference is at the large scales. And also these bottom spectra can be shown in the spherical wave numbers. Okay, so now what is one interesting question is once we split the circulation into Rossby modes and non-Rossby modes, we can ask now how much these non-Rossby modes, I was talking earlier about the Kelvin wave, how much these non-Rossby modes contain how much divergence do they contain, and this is what is presented in this figure. So figure on the right is showing kinetic energy, total kinetic energy of the horizontal circulation at some level over a week, and then figure in the middle is showing irrotational and non-divergent parts of only Rossby modes, where divergent part, the blue spectrum, is of course negligible. But the figure on the right, it is one I'm interested in for my large-scale tropical trends. This is the divergent and rotational part of the non-Rossby mode energy. And here encircled in yellow are the large scales. And at this particular level, you see that vorticity and divergence contribute about equally at zonal wave number 1. At other wave numbers, divergence dominate, because this is a level, I think, near around 250 hectopascals, but the same spectra lower down are actually then more dominated by the vorticity. So the partitioning between vorticity and divergence in the tropics depends a lot on the level. Okay, so once we have this half wave number filtering in terms of half harmonics, we get these spectral expansion coefficients that are defined by 3 component wave number. And because the composition is 3D orthogonal, one can then do all statistics in spectral space. So one can compute energy at a single time step, time averaged energy of the time average state, which is E, and then one can evaluate temporal variance or transient energy for every wave. And then we have, assuming ergodicity, we have this relationship at the bottom, which is coupling transient and mean energy. So, and these are then used later, I think, in the talk by Yuan Bing. Okay, so now going back to my original question. So what I showed by these figures from Adrian Simon's paper are trends in the mean state. But what I will show next as a result is something else, are trends in the variability. But then this is just one step towards understanding these trends in the mean state. So to understand trends in variability, we have applied this wave number filtering to the 4 reanalysis data, all 4 major reanalysis data sets over 35 years, and then computed sub-seasonal variances in every scale, and then evaluated their trends. So let me show you what it looks like for the large scale tropical circulation. What is shown in this figure is SSVI, this is the sub-seasonal variability integral. And this means that for every season in every reanalysis, we compute the sub-seasonal variance. Okay, so we get the time series of these sub-seasonal variances, and then we just took the square root after integrating them in the wave number space. So this is the integrated square root of the integrated variance, and then we take then we have the 35-year mean of sub-seasonal variance, and then we take deviations from that. So what is plotted here are deviations from that 35-year mean for every season, and then there are 4 curves, one for each reanalysis data. And what is plotted are just 3 modes: Kelvin wave, mixed Rossby gravity wave, and the lowest of the westward propagating inertia gravity waves. In this case, 0 exists only for these VIG, so it's just the wave numbers 1 to 5. So if you look at this plot, I'm not sure if you would agree, but you see towards the edge that the amplitude of the sub-seasonal variability is increasing, and just getting more positive. But if I compare this, for example, now with the middle latitudes, what you see there, that reanalysis agree much better with each other, so the curves sit on top of each other. But for example, if we go to the subtropics, because this is now large scale N1 Rossby wave, which is zonal wave number 3, you see the discrepancies between a subseasonal variability. So this is measuring a certainty that we have in the description of circulations. And then we computed trends by doing linear fit and then again plotting these deviations, and significance is everywhere where you see cross, and it is tested by the modified Mann-Kendall test. So basically you see that in era 5, they agree in all seasons that there are positive trends, almost up to 20% in subseasonal variance in these meridional mode 0 and 1, and those are modes I showed earlier in time series. While in the smaller scales there are negative trends, but smaller scales are not reliable because other reanalyses may have different results, and this is what we actually show by comparing era E and era 5, but we explained why is that, because era E was less reliable in the stratosphere. So now, because of the lack of time, I will just mention that they agree, all 4 reanalyses agree very well about the trends in the extratropical Rossby waves that is presented here, and all details are in the paper. Okay, so now I go back to those plots by Simons, and I would like now to really say again that what I just showed is just part of the story, because we don't really understand how much of these trends are associated with the balanced circulation, with the divergence dominated or vorticity dominated circulation, and the extent to which the trends are also coupled to the trends in the extratropics, even they may not be statistically significant here. This is also something that still has to be understood. What I will show in the last slide is really the variant, the extent to which the tropical interannual variance is also projecting on these non-Rossby modes. So first here, so we can look at this is a subset of the CMAP5 EMIP simulations, and we look at the interannual variability associated with Rossby waves. What you see here, this is in zonal winds in meter per second. So there is a relatively good agreement, but I would like to just point out that that interannual variability over, except here over West, Central and Eastern Pacific, is between 2 and 5 meters per second. And this is just as much as the amplitude of the interannual variability in non-Rossby modes in these models. And here the bottom left figure is for the era interim. Okay, so they differ between themselves, they differ from era interim, but about half of these even interannual variabilities is in unbalanced circulation, and this is because the Hadley cell and to some extent also Walker circulation, they project onto these non-Rossby modes. Okay, so this brings me to my summary. So I have tried to argue in favor of a global measure of circulation variability that is informative both about scale and regime, and this is the multivariate mode decomposition. I have shown that there is a positive trend in the large-scale subseasonal variability in the tropics that 4 reanalyses agree about. And Jana Strigunova will talk on Thursday on how she used this approach to analyze Eurasian heat waves. I would also like to say that all these data we have in a space of half harmonics are available. If someone is interested, please reach out to us. And that the same approach has been extended to analyze what we call biased teleconnections, which is what Yuan Mingzhao will speak about next. Thank you very much.
Okay, thank you very much for this great talk. Are there questions either here or online.
Yeah, I suspect nobody really listening has used
No,
this
there's
composition.
a question. It's just that somebody was coming up. Sorry, they need to get closer to the microphone.
Yeah, sorry for being so slow. But, thank you very much for your interesting talk. I was wondering how well the vertical mode decomposition works, given that we have topography all around the globe, and I think I remember from class that the vertical mode decomposition can be difficult if there's topography.
I'm sorry, I have difficulty in understanding what you are saying. I heard only orography difficulties.
Maybe you can come a bit closer.
Okay,
The mic is here.
Okay, I'm sorry. So how well does the vertical decomposition, the vertical mode decomposition work if there's topography? And the second question I'm having is, I think these U modes rely on the assumption of linearizing about the state of rest. And I think in particular for vertical wave propagation, the background wind is really important. So I wonder how well the vertical mode decomposition works in general.
Yeah, so the all results, thank you for this question. So all results that are presented use decomposition in the terrain following coordinates. So the effects of topography are included. And actually, if I show, or if you look online or in some other paper, results that are in the lower troposphere, we can see everywhere this of the topography projecting on the IG inertia gravity modes. So it is not a problem. There is also an approach to do this decomposition in the pressure system that we also, which is more common in climate research, that we also use. But yeah, we don't have such a large full analysis intercomparison in pressure system yet. So what is not making this projection 100% complete in the lower troposphere is the need to reduce vertical truncation because of the way the vertical structure equation is solved. But yet, you know, the composition in the upper troposphere as above is perfect because, yeah. But your other question is also very relevant. It is the question on the effects of the background flow. So I would like to point out that that we are projecting that this decomposition, you know, it's a just projection on the spatial structures, and these structures have to be the structures with respect to the state of rest, because we need a stable basis functions solution. Also, the horizontal structure of or the meridional structure of half functions is not very sensitive to the background for the large scales. For the smaller scales, it is of course different. But I mean, there is a number of studies using this approach to study the wave propagation, you know, through the shear flow. So one just has to take into account that the waves are propagating through shear flow. So it's not really a shortcoming. It's not any reason to prevent someone from using this kind of decomposition. Did I answer your questions?
Yes, thank you very much.
My pleasure.
Yeah.
Thank you for your interesting talk. So my question is related to the increase in variance that you showed that has happened in the recent decades. Does this in any way translate to, or does this explain the changes in synoptic activities like cyclones or trends in ENSO? I mean, is this related, the increase in variance in the different modes that you showed? Is that related to the changes that are observed?
So, yeah, I understand your question. So, but probably I can't answer it. So, there is one study, to my knowledge, that has looked into trends directly in the satellite radiances or brightness temperature, and then related these to different equatorial waves. and they reported similar results, which means positive trends in the large-scale equatorial wave activity. So how does this come to synoptic processes in the tropics? I don't know. To my knowledge, and I actually is based on indirect reading. Yeah, also Adrian Simons is discussing it in his paper. No much discussion of these strengthening of tropical easterlies in the IPCC report or the literature. So I don't know. Maybe someone else in the audience can answer.
Maybe later in the discussion.
I have another question, if I may. Any comments about the moist coupled waves, like the MJO, for example?
Yeah, so MJO is not a normal mode. Yeah, so in our decomposition, in this decomposition, of course, it will project to some extent to the Kelvin mode, and then these, you know, these jars away from the equator, they will project on N1 equatorial Rossby wave, but it's not a normal mode. So yeah. Okay. Maybe if you are interested, we have some analysis of how this projection works in case of Kelvin wave, and in the last year Journal of Climate paper. Yeah.
Okay, thank you.
Sure. Then we'll take just one more, and then we'll leave the others. Yeah.
Hi, thank you for the talk. Well, I have a question about, I'm working on geopotential high time series, and the filtering system for geopotential high data in order to obtain anomalies are mostly done with like subtracting running means and things like that. And I'm wondering if this method is like a better way to decompose the signal in order to obtain the parts that we really want to subtract, like the seasonal variability or reference climatology. So in order to obtain a more like robust method to always subtract the parts of the signal that we don't want to analyze, which is better than like subtracting running means of different length. I was wondering that if there is an application.
Thanks for the question. So I'm not sure I understand all, but I mean, if you don't mind, would you mind sending an email? I would be happy to engage, you know, to discuss this with you via email.
Yes, for sure. Thank you so much.
Thank you. Thanks, everybody.
Okay, thank you so much. And if you remain online, I'm sure that there will be other questions during the discussion at the end. And so our next speaker, as already introduced by Angelica, is Wenbing Zhao from the University of Hamburg. Sorry for mispronouncing your name. Talking about global responses of the atmospheric circulation and its variability to regional SST anomalies.
Okay, thank you. Can you hear me?
Yes,
hello.
We can hear you.
Oh, okay. Let me share my slides. So can you see my slides?
No.
No, not yet.
No.
How about now?
No, not yet.
Let me see.
Yes, now we can see it.
Okay, let me go to the presenter mode. So is it in the presenter mode?
Yes.
Okay, here we go. Hello, everyone. My name is Yuanbing. I'm from University of Hamburg. First, I would like to thank the organizers for giving me this opportunity to present my results. Today, I would like to talk about the global atmospheric responses to regional SAT biases. with a particular focus on the circulation and its variability. We know that coupled climate models suffer from notable assertive biases almost everywhere in the oceans, and understanding the effects on simulated atmospheric variability is very important for the uncertainty quantification of the climate projection. Although many studies have been done in this direction, most of them focus on their local impacts. However, regional assertive bias can also have remote impacts on the model circulation and its spatial and temporal variability, which we refer to as the bias teleconnection. It's for sure that bias teleconnections depend on the location of the assertive biases, but we don't know exactly how. So here I'm asking, how do bias teleconnections caused by regional assertive bias depend on the location of the latter? So to answer this question, we carried out a series of century-long simulations with a general circulation model PLASIM. It includes a control simulation, which is forced by the monthly assertive from the era 20th century reanalysis, and 106 sensitivity experiments. In each of them, the model is forced by a Gaussian-shaped positive assertive bias somewhere superimposed on the same monthly assertive from the as in the control run. Here shows an example where the assertive bias is placed in the Central Pacific. That is to say, the discrepancy between the sensitivity and the control simulations is entirely due to the assertive bias. And now let's first look at the atmospheric response. This plot shows the time mean responses, namely the model biases of the precipitation and the geopotential height in Boreal winter time from 4 experiments. 2 of them have the assertive bias centered at the equator, and the other 2 has the assertive bias at the 30 degrees north. The precipitation is shown by contours, and the geopotential height is by shadings. So we can see that the response depends on the location of the assertive bias. When the assertive bias is at the equator and it results in strong precipitation response, and which produce bias teleconnections in the global circulation. In contrast, the response is very weak when the assertive bias is in the extratropics. Moreover, the response is also sensitive to the zonal location of the assertive bias, and we see that the bias teleconnection caused by the assertive bias in the Pacific warm pole is much stronger than that induced by the assertive bias in the Indian Ocean. So all these indicate that the circulation response to assertive bias is modulated by the local background state. And we will come back to this later. The circulation variability is much more difficult to evaluate. In this study, we use the model decomposition, which has been introduced in the previous talk by Nadika. And with this method, it's very easy to quantitatively evaluate the energy, namely the spatial variance and the interannual variance of the circulation in different dynamical regimes and across scales. In this talk, I will focus only on the globally integrated wave energy and the interannual variance. So the zonal mean modes are not considered. So when there is an assertive bias, and it will lead to changes in the globally integrated wave energy and the interannual variance. And we calculate the changes, and we got the 2 values, 1 for each, because they are globally integrated quantities. And we draw the values on the map at the location of the SAT bias, like this. And the values here, the changes here is the relative changes with respect to the reference state. And the same is done for all the sensitivity experiments. And we obtain these two maps. The left panel shows energy changes, and the right panel shows changes in the interannual variance. So the red colors mean increases, and the blue colors mean decreases. Please note that every dot here shows the global response, not the local response. And we see that, firstly, the tropical SAT biases cause much larger changes in the global variability than the extratropic SAT biases. Secondly, the intensity of the response seems to depend on the background SAT. The black contours here shows a background SAT above 25 degrees, and we can find that the warmer the background SAT, the stronger the response. And we also see that the sign of the response varies across ocean basins. For example, the SAT bias in the Pacific warm pole increases the wave energy and the interannual variance, but the SAT biases in other tropical oceans decrease them. So there are two follow-up questions here. Why does the response depend on the background SAT, and why does the sign of the response vary across ocean basins? To answer the first question, we first calculate the background SAT within the SAT bias region. And this plot shows its relationship with the absolute changes of wave energy and the interannual variance. And we can see that the response stays at a low level when the background SAT is below 25 degrees. Whereas above that, the response increases abruptly. So it implies an SAT threshold of roughly 25 degrees for substantial response. In addition, the dot colors here indicate the central latitude of the SAT bias. And we found that all the strong responses are caused by the tropical SAT biases. And this reminds us of the relationship between the SAT and the deep convection in the tropics. Previous studies have shown that the deep convection substantially increases with SAT from 26 degrees up to about 30 degrees. So one hypothesis here is that the positive SAT bias added to this threshold triggers or enhances the deep convection, and which results in strong responses. To verify this, we calculate the local precipitation changes because it implies changes in the convection. And this plot shows its relationship with the local background SAT. And we can see that when the background SAT exceeds 25 degrees and the positive SAT bias added to it leads to a large increase in the precipitation, and which eventually results in strong circulation and variability responses. So it verifies our hypothesis. As for the second question, namely the dependence of the response on the ocean basins, and let's look at the energy changes due to the SAT biases in the tropics, where the amplitude is large. As introduced in Nadika's talk, the energy changes can be separated into two parts. One is the bias variance, and which is determined by bias amplitude, and the other one is the bias covariance, which is related to bias phase. The bias variance is positive by definition. For the bias covariance, it has positive responses to acetic bias in the Western Pacific, whereas it has negative responses to the acetic bias elsewhere in the tropic oceans. Therefore, it's the bias covariance that explains the variation of the signs across ocean basins. But what's the underlying physics? So it should be related to the interaction of the circulation bias with the background state, such as Walker circulation. We know that the Walker circulation has its ascending branch in the Pacific warm pole region. And positive acetic bias within this region cause circulation biases that are in phase with the Walker circulation result in the positive response. Whereas the acetic bias far away from this region induce the circulation bias that are out of phase with the Walker circulations, so resulting in the negative response. But this is just an argument. A full understanding is yet to obtain. To conclude, we found that the biastatic connections caused by regional acetic bias depend on the location of the latter, and the response intensity depends on the background acetic, which is related to the acetic threshold of the deep convection. And the response is also sensitive to ocean basins, which set the phase of the circulation bias. Please note that here, all the response mentioned is for the wave circulation. The zonal mean circulation is not considered, but actually we can evaluate any component of the circulation. In our recently published paper in weather climate dynamics, and we studied the impacts of the tropic Indian Ocean acetic bias in different dynamic regimes, and for the tropic and extropic circulation respectively, and we found some difference among them. So they provide more information. Okay, I will stop here. And thank you.
So, any question for Yang Bing?
Yeah. Thank you for the talk. Mine is more of a technical question. So
okay.
I was wondering if you can detail a bit on what you mean by when you refer to energy, and yeah, because I'm always a bit puzzled when I mean, I remember that when I was using plugin with 10 vertical levels, the energy conservation was always a bit challenging. So maybe it depends really on what you mean by energy.
So thank you for your question. It's a very good question. So yeah, we checked the energy conservation in the plugin, and it's I would say that it's the total energy is conserved, and here in my talk, the energy is calculated for the kinetic energy and the available potential energy.
Okay, thank you.
And I also had a question. So can you use any of this to understand biases in complex climate models? And how, let's say, how would you use this?
Thank you for your question. So far, I haven't applied this method to the more complex models. Yeah, but I want to say that the application is the same, because the application is only for the model output. It doesn't matter what model you use. Do I answer your question?
Yes, sure. Thank you. Yes.
Hi, thanks for your talk. So with climate change, the ocean will warm, and there will be more location that will be near to this critical threshold. So do you expect somehow that the effect of the biases in SST will be stronger on the atmospheric circulation? So in a way, these biases will increase because of climate change. Is there any way you plan to look at that? Thanks.
Okay, it's a very interesting question, but I'm not sure if I can answer your question. So as you see that the threshold, so the threshold is related to the deep convection. If the SAT threshold for the deep convection changes under climate change, and I think the threshold for the substantial response will also change. But I didn't do that. It's just my opinion.
A final question?
Thank you for the interesting and useful, very interesting stuff. So my question is related to your biases. The perturbation that you imposed is positive. What happens if the perturbation is negative?
Yeah, very good question. Actually, we also did that for both the positive SAT bias and the negative SAT bias, and I can maybe I can show you the slides if I can.
Quickly ask a related question. The CMIP models have simultaneously positive and negative biases in different places. So any comment on that? How your results will change if you have a positive bias in one place, negative bias in another place? So both related questions.
Oh, it's a very interesting question. I don't have at the moment I don't have the answer to your question, but I think it depends. It depends on the it depends. Sometimes they may have the so they may be enhanced by each other, or they may be cancel out by each other. This is my okay. This is just my thinking. I don't have a clear answer for that, but it's a very interesting question.
Okay, great. Thank you so much. And
Thank you.
now it's Valerio's turn.
Yeah, sorry, you'll have to see my emails for a second because there
He
was.
needs to update his presentation, and he's going to be talking about the relation between extreme meridional energy transport, modes of circulation, and heat waves in the Northern Hemisphere and mid-latitudes.
Okay, so let's go back to the screen sharing. Huh? Okay. Yeah. Thank you very much. I wouldn't say for having me here, but for being here. Yeah, this is something I want to share with you for the sake of discussion. It contains a bit of some previous work that has been carried out both when I was a postdoc in Hamburg in Valerio Lucarini and then Gielka's group, and then here in at ISAC CNR. And it contains hints and contributions by some people I want to mention: Federico Fabiano, which is a colleague here, Davide Faranda from IPSL, Melinda, who is in the audience, Gabriele, who talked before, Rune Gravesen from Tromsø, and yeah, as I said, Valerio Lucarini, Luca Famos Paolini from CMCC, and Flavio Pons from IPSL as well. So this starts from what Nedelka kindly introduced, that was the one-dimensional FFT decomposition of fluxes in the atmosphere, and in particular meridional energy transports in the atmosphere. And this decomposition, which is basically based on Fourier coefficients, was carried out, implemented by Rune Gravesen and his group in a paper from 2016, where basically he was showing that if you decompose the annual mean meridional energy transports in different zonal wave numbers and you sum up them successively, and if you focus on the mid latitudes, you will see that basically the energy transport is somehow equally partitioned between synoptic scales, so to say 6 to 10 zonal wave numbers, and planetary scales, so to say 1 to 5 zonal wave numbers. And of course, there's the negative contribution, at least in mid latitudes, by the zonal mean circulation, which is basically the signature of the feather cell. We implemented this in 2 dimensions, meaning that we carried out the zonal wave number decomposition latitude by latitude, and instead of looking at the annual means, we actually took all the 6-hourly data that we could find in ERA 5, and we provided a probabilistic distribution of these values latitude by latitude. And what we see here actually is that, it is true that the synoptic scales and the planetary scales are somehow equally partitioned, but they actually have a very different meridional distributions because the synoptic scales are peaking around, let's say, 38 degrees north, whereas the planetary scales are peaking around 55, but also that the meridional spread within the mid-latitudinal channel, so to say between 30 and 60, is much larger in the synoptic scales than in the planetary scales. And also we performed, we implemented we retrieved the PDFs of the extremal transports, so the extremely strong, or in other words, poleward transports, and extremely weak or equatorward transports in the meridional energy transport, and we looked at the contribution of the different wave numbers or groups of wave numbers for these extremes, and we noticed that basically, at least in winter, the contribution by the planetary scales to both tails of the distribution is much more even than for the synoptic scales that are actually contributing much more in the subtropical part of the mid-latitudinal channel than to the higher latitudes. We started from this, and we wanted to understand what these extreme transports in terms of meridional energy transports were looking like in terms of dynamics. So we took the usual k-means clustering for 3 different regions, the Eurasia and Atlantic, the Pacific region, and the whole of the Northern Hemisphere mid-latitudinal channel. And we received the weather regimes that we all know, at least for DJF, that in the East Eurasia and Atlantic region are the NAO plus, Scandinavian blocking, sorry, Atlantic region NAO minus, and for the Pacific are the Pacific trough PNA plus, PNA minus, and Bering Ridge. I will focus on these ones because basically this is a repetition of what we see regionally. And we see that if we focus, for instance, on poleward extremes, there is a significant increase in the occurrence of NAO minus, or in other words, AO minus regimes compared to to all the occurrences, and a significant decrease in the NAO plus or Bering Ridge and Aleutianian Ridge occurrences compared to the overall population. So this is to say that basically when you have an extremely strong poleward, extremely strong meridional energy transport in the Northern Hemisphere mid-latitudes, this is typically associated with some sort of blocking in the Atlantic region. For summer, the picture is a bit different, but not so much actually, because the regimes that are standing out, so to say, are EATC2, which looks like a bit as a Scandinavian blocking in winter, and NHC4, which is pretty much similar to EATC2, meaning that basically you are having stronger than normal transport in the Northern Hemisphere mid-latitudes when there is another kind of blocking, which is more zonally distributed, but still it is carrying out cold air towards the Mediterranean region, and features a low pressure systems over Greenland. Then we provided composites of SST. This was kindly provided by Luca Famos Paolini from CNCC, where we are showing that basically the signature of the meridional energy transport in SSTs is actually more relevant in the Pacific than in the than in the other basins, and it is pretty much the opposite. The patterns are pretty much looking opposite in DJF poleward extremes compared to JJA poleward extremes, where basically we have cold anomalies over the western coast of the North America in winter, and cold anomalies in summer. And this is something that actually we started thinking about, and we are still thinking about, as this is a work in progress. And the other side of the medal, let's say, is looking at the occurrence of heat waves. And basically what we are showing here is how, what is the composite mean of land surface temperature within the population of, in this case, equatorward weaker than normal transports in winter. And we are highlighting those regions where this composite pattern is different from what you would have if you would have a heat wave in winter. And we clearly see that not only from the point of view of temperature, but also from the point of view of pressure, the signature of this weak meridional transport is an excess zonality, basically, because pressure systems extend much further into the continents, and warmer LST anomalies that are associated with heat waves are spreading toward Eurasia within continental Siberia. And this is also something that you can see if you count basically how much more frequent it is to have a heat wave in the population of equatorward or weak meridional transports compared to a normal occurrence of heat waves in the overall population, where you see that basically the abnormal occurrence of heat waves is occurring here in the Eastern Europe toward Siberia, and also in the most part of China. But also, actually, it is pretty much relevant in the central North America, because this is I would say coherent with having some sort of blocking in the Central Pacific. Yeah, I think I will skip this one because it is basically saying some similar things about JJA, and I will jump into the summary what the take-home messages are of my short talk is that the meridional energy transport extremes are linked to planetary scales everywhere, whereas they are linked to synoptic scales in the lower part of the mid-latitudinal channel. That high latitudinal blockings are favored for stronger transport in DJF, whereas what I mentioned as mid-latitudinal blockings, or at least zonally distributed blockings, are favored for stronger transport in JJA. And heat waves are more frequent for extremely weak transports, and this is a signature or an enhanced zonal circulation in winter over most of the Northern Hemisphere continents. What is the role of Pacific SST anomalies is something that we are still looking at, and it might be some source of discussion for this workshop. Thank you for the attention.
Thank you, Valerio. Any questions for Valerio? I have a super quick one. When we're comparing the Pacific SST anomalies in summer and winter, you mentioned that they look like opposite sign. But to me, the one in the, and I don't know if this matters, but the ones in the summer also look a little bit more zonally oriented. Well, sorry, less zonally in the summer, right? They have some more zonal structure. I don't know if that.
Yeah, that's true, but I mean, they are opposite sign basically.
Sure.
Yeah, that's that was my point.
Okay.
But yeah, that's true. That
Adrian, can you come closer? Sorry, so that people. Let's try. Let's see if I hear.
It was just related to that. It's difficult from that projection to see also if you've got a signal around the equator, the equatorial Pacific, because you were emphasizing the North Pacific. But from that projection, I'm not quite sure exactly if that's also a strong equatorial signal.
Yeah.
Let me repeat the question. Adrian is asking if there is any role for changes in SST over the equatorial Pacific.
Yeah, well, that's something we are actually investigating because we are trying to perform some lead correlation of meridional transport extremes with the ENSO signal, but so far results have been quite inconclusive. That's why I'm not doing them.
Michele, can you please also remind? Young people are not allowed to be lazy.
Hi, Valerio. I have a question. Or someone, sorry, I haven't seen it.
Anna, we'll take your question. Sorry, Michele.
Yeah, I mean, it's okay. I can ask after.
Yeah. Okay.
Yes, I was just wondering what's the causality relationship here. So I was wondering, well, is it blocking that alters the energy transport as a part of the wave signal maybe, or it's something that changes in the energy transport, maybe in the tropics, as you were saying, maybe it's connected to what Adrian was asking, that then make more, likely the atmospheric blocking to develop.
Yeah, but yeah, as you know, correlation doesn't mean causation, so that's we have to be very careful with that. But I think this goes pretty much towards what Gabriele was saying at the beginning of the workshop, where he was, basically showing some features of the Atlantic variability, where you basically have some precondition that relates what happens in the North America with Western Europe. And I'm not saying that this could provide an answer to that question, but I would say that in order to explore causality, we could proceed the way it was suggesting to proceed.
Thank you.
No one.
Great. Jana, you had a question?
Yeah, thank you very much for this nice talk, Valeria. I was just wondering, just correct me if I'm wrong. So according to results, blocking is associated with stronger meridional transport, while heat waves, which is considered to be part of dynamics or related to blocking, is associated with weaker transport. Would you comment on it, or it's still unclear?
Yeah, well, the point is that what I was showing was DJF. And I mean, you might say that, I mean, at least when you're looking at global scale LST anomalies, what matters is what happens in Eurasia. And I mean, how large is the snow covered region in winter is what matters. And if you have increased zonality, which is, I mean, related to weakened transport in my interpretation, you have, I mean, stronger oceanic currents entering deeper into Eurasia, which decreases the snow cover. That's why it is not straightforwardly related to a blocking interpretation, let's say.
Okay. So you want to say that dynamics is not that straightforward as we would think for case of summer?
Yeah.
Okay, thank you.
And summer it's a bit more complicated, but also because what I have had no time to show is that different weight numbers are excited, so to say, in summer than in winter, and typically there are higher weight numbers.
Okay, thank you.
One final question?
Just a very short comment or a suggestion. It would be really nice to see this for summer.
Yeah, I will focus on that.
Heatwaves and blocking, and especially for me.
But that was the easy part, you know. Yeah.
Okay, great. Thank you, Valerio. And now we have another in-presence talk by Paolo Ghinassi. He's going to be talking about a method for identification and tracking of Rossby wave packets based on local wave activity and application to verify reanalysis data.
I don't know why I stopped sharing, but here it goes again. Okay. Yeah, sure.
Right, so I'm going to talk about some work that I started doing with Giuseppe and Susanna, my colleague here at ISAC CNR. And so the idea is that during my PhD, I developed a diagnostic for wave packets, which is based on local wave activity in isentropic coordinates. So the idea of local wave activity is that it is a field which is proportional to the waviness of your potential vorticity field on a given isentrope. And so, as Jacopo first introduced the concept of equivalent latitude, so at each latitude circle, you basically associate a PV contour such that the two spherical caps, they enclose the same mass, and then you integrate over the meridional direction at each longitude the potential vorticity anomaly. So in this way, the wavier are your PV contours, the stronger is your potential vorticity field. To compute this local wave activity from data, what do you need? You need UV and temperature on some pressure levels. That then this data will be interpolated onto isentropic surfaces. I used year 5 data from 1979 to 2021 to test this, and with the spatial resolution, I tested the 1 times 1 degrees, but even 2 times 2, it works, and 6 hourly data. And then the idea is to combine the local wave activity field with the tracking algorithm. So once the wave packets are identified, then we want to follow them in time and compute the trajectories. And to do that, I combined the wave activity diagnostic with the track, which is a tracking algorithm made by Kevin Hodges. So how the local wave activity field look like. So we started from a potential vorticity field. So here we have a snapshot of a potential vorticity on a given date or on a given isentrope. And well, here you see that here you have a hint that it may have a wave packet because you see a series of trough and ridges over here in North America. Here is the resulting local wave activity field. And you see that you've got some signal whenever you have a ridge and a trough. But then the local wave activity, of course, it is still contains the phase information of your waves. And then to remove it, we apply a zonal filter to the, let's say, raw local wave activity field in order to smooth it along the zonal direction. And instead of a series of ridges and trough, we want to be able to get the wave packets as a single structure. So here you can see basically the filter, the resulting filtered field, how it looks like. So then the idea is to apply trackers, so to compute trajectories for these wave packet objects that then they propagate along mid-latitudes. And here is how the climatology look like. Here on the top panel we have the track density, and you can see that you can clearly see the main storm tracks. Here you have a maximum in the North Atlantic. Here's the North Atlantic storm track, and you can see the Pacific storm track, which appears to have two local maxima, one here in the upstream part over Japan, and another maxima here, say upstream from the Rocky Mountains in the West Pacific. And here the amplitude, sorry, these are data for the winter season, I forgot to say. So basically here the Rossby wave packet amplitude, or basically the maximum, the amplitude maxima of the wave packets which we are following. And you see again a huge blob here over the North Atlantic, and another one here over the Pacific. And if you see here with these wave packet maxima, they seem to be a bit shifted to the north compared to the tracks, which probably means that the wave packets with a larger amplitudes, they tend to be shifted a bit northward with respect to the main track. Here you see the genesis and Lysis density, or the regions in which these objects they originate. And again, here you see mainly the upstream and the middle part of the Atlantic Ocean. And then again over the Pacific, you have two maxima. One here over, say, Eastern Asia, and another one here over the Pacific. And the Lysis density is two clear maximum, one here downstream of the Rocky Mountains and over Europe, which are regions of frequent wave breaking and wave packet decay. So this was basically how the climatology for wintertime looks like. Then we start to do some very, very basic analysis. So we apply these tracking algorithm and the diagnostics to reanalysis data. So we divided these 40 years of reanalysis that we considered in two periods. The first spanning 1979 to 2000, and the second one from 2000 to 2021, I think I took it. And then we looked at the differences. So here are the differences in the track density, and oh yeah, all the differences they have been scaled by the standard deviations computed over 40 years, basically to see the magnitude of the difference scaled with the interannual variability, basically to see whether the two magnitudes are comparable. We can see that, for example, for the track density here in the mid-latitudes, there is a hint that there is a northward shift of the tracks, especially here over the Atlantic, but also here over the Pacific. If we look at the wave packet amplitude, we see some signal that there is an increasing amplitude here over Greenland, for example, and here over Alaska, so in the northern latitudes, and a decrease in here north to Scandinavia. And again, here again, I show you the amplitude difference, but here instead in the bottom panel I have the mean lifetime. So basically how long these wave packets live. And so the interesting thing here is that you see that here over Greenland, where you have an increase in the wave packet amplitude, you also have an increase in the mean lifetime, whereas here over Scandinavia you have a decrease of the mean lifetime. So this probably suggests that Greenland is a region where you have more high amplitude, long-lived wave packets, that they could be large amplitude eddies, even blockings maybe. Whereas over Scandinavia, the opposite is happening. Here for the Genesis density, you see again that there is a tentative evidence that we have less genesis of wave packets over the subtropics and the southern latitudes, and an increase of the wave packets genesis over northern latitudes, for example, here over Alaska, or here over Canada and downstream of Greenland. And then what we looked at is on how the El Nino, so the ENSO, can have an influence on the Rossby wave packet tracks. So here we had the look on the trajectories, but unfortunately this doesn't look, it looks a bit noisy, the resulting plots. This may be due to the fact that we didn't consider all the analysis that we have, and maybe the spatial resolution is a bit coarse, but anyway, here is basically the tracks of all El Nino of positive ENSO years compared to basically the neutral ENSO years. And so you see that in these years, with El Nino years, you tend to have basically more tracks here over the eastern coast and in this part of the Atlantic. Whereas in the linear years, so the negative, during the negative ENSO phases, one region in which you tend to have more tracks is here the Northwest Pacific, but also here the southern latitudes of Western Europe and the Mediterranean. And then you tend to have less tracks over the higher latitudes, both in the Atlantic and over Europe. If we then look at the amplitude, the picture is a bit clearer, and if you see that during the Nino year, you tend to have higher amplitude wave packets in northern latitude over the North Atlantic, and lower amplitude here over Alaska. Whereas the opposite is true for La Nina year. And then we looked at summer, so we went to higher isentrope to basically intercept the PV gradient on a higher isentrope, but of course everything looks a bit weaker. You see that the storm tracks are not neat as in winter, and also if you look at the amplitude, there's basically a weak, more uniform belt of wave packets. And if we then look at again at the differences, we see again a north shift of the storm track, especially evident in the Atlantic. If we look at the difference in the amplitude, there's nothing really significant apart maybe from here region over Scandinavia in summer. It seems to have a higher amplitude wave packets. So yeah, this was just a very application of a diagnostic tool that of course can be improved for sure and applied to do more complex or robust analysis. And here I basically summarized the results that we found in the analysis data for winter and summer. And yeah, that's basically it. Thanks.
Thank you. Questions for Paolo? Would you mind, as always, please? Come forward.
Yeah, thanks for this nice talk. What's the motivation of developing this new diagnostic, given that there's Rossby wave packet climatologies that have been published and investigated previously?
Yeah, the thing is that they mainly the diagnostics they are based on the envelope of the meridional wind, and which basically assumes that your wave packets are wave-likes and so of small amplitude. The advantage of using local wave activity, and that's a good question because I forgot to say, is that it is of course valid even when your wave packets they become of large amplitude or finite amplitude. So what happens is that when you look at how these wave packets are in reanalysis data or in state-of-the-art models, they may deviate quite substantially from a wave-like structure. And if you apply the envelope of meridional wind, or for example, the Fourier decomposition on some wind and origin potential spectra, then you have that these wave packets, they may break, they may do some weird things, whereas a local wave activity, I think it is a better quantity to identify and follow them because it keeps the information given its space from on integrated PV. So basically, and you can use it for whenever, whatever wave-like field. It keeps your information. It tracks your object for longer time. I would say.
Thanks.
Lenka. Lenka first.
Oh, Lenka, sorry, I didn't see you. Sure, go ahead.
Ah.
I don't know, we'll see.
You can give a try, and if they complain,
daily physical activity, standing up and coming here.
Yeah, so thank you for the very nice talk. I was wondering, so a lot of the patterns that you showed, they seem to go with the kind of overall expected shifts in the jet, say for and so shifts and things like that. Are there any kind of surprising aspects of this? For me, one of the surprising ones was the genesis and lysis of the wave packets, where looks like there was an asymmetry between where it happened in the Pacific and the Atlantic with respect to the storm tracks. But maybe that's something.
No, that's actually a good point that I haven't noticed. Actually, the northward shift of the storm track was very evident, and I think it agrees on what is found in the literature recently, looking at the analysis data, for example. But no, I haven't made any consideration about the genesis and lysis regions. I think I haven't shown the lysis regions, for example, in the differences because they were I couldn't find really a clear pattern. But in the genesis, for example, you can really see that you, for example, have less genesis in the subtropics, pretty much everywhere, and more genesis in actually up to very high latitudes. So yeah, that's interesting actually, and I haven't made any argument about it. But thanks for pointing this out.
Sure.
Sure. Okay.
Well, yeah, we're eating into the discussion time. We'll try to cut it. I mean, part of the nice thing of the workshop is that there is time for questions and discussion.
Okay, great. Thanks. Yeah, it was more a sort of curiosity. You talk about next possible application. What do you have in mind? For example, linking the packages to heat waves, so variables at 2 meters.
Yeah.
At the surface, let's say.
Yeah. Actually, it would be interesting to see whether, for example, wave packets may act as a precursor of something else, like if they, for example, may trigger, I don't know, heat waves or whatever, some persistent weather patterns, or for example, blocking that, as Jacopo and Gabriele were talking before, may be linked with some upstream wave activity coming. So yeah, the idea, of course, is to apply this method to some more complex cases, and so now we just tried it, and then next step is to apply it. Yes.
Questions online?
Oh, maybe 1 second.
Let's not forget them.
No.
No. Okay. Thank you, Paolo. Okay, so we're getting now to the last talk of the day by Asaf Ockman from Hebrew University of Jerusalem, with a question as to whether Atlantic European weather regimes exist. Thank you, Asaf.
Okay, can you hear me?
Yes.
Okay, and can you see my slides?
Yes.
Okay, cool. So thanks everybody for staying for the last talk. I know it's a long day, so thanks a lot. I'm sorry not being able to be in presence, but as you know, Israel is now at a state of war, and everybody here tries to contribute his part. Okay, but anyway, we will talk about science at the moment. So this talk will focus around the question, do Atlantic European weather regimes physically exist? Basically, the take-home message from this talk is that they actually do. And if you need to go home now, so you can actually go home. So weather regimes were introduced already in the 1940s, of course. They were used for sub-seasonal to seasonal predictions, improvement. They were used for understanding how the large-scale circulation influences surface extremes, and also have been used to understand how climate change will influence the large-scale circulation. But since the seminal work of Devoret and Charny in the late 1970s, it has been debated if they actually are a physical entity. Okay, and what do I mean? Actually, if they are quasi-stationary, persistent, and recurrent metastable states. Okay, and we will try to answer this question. The slide change now. Do you see my second slide now?
Yes. Sorry.
Okay, perfect. Perfect, thank you. So basically, we use two methodologies to try to answer this question. One is just a statistical classification based on EOFs and k-means clustering, introduced by Grams et al. In 2017, which classifies the Atlantic European geopotential height at 500 hectopascal into 7 distinct weather regimes. You can see their names here. Okay, and you may know this classification. This classification uses a weather regime index, IWR, which was introduced in Michel and Riviera in 2011. And actually, what this weather regime index it tests how strong the weather regime is projected onto the climatology. Okay, so if we look at this figure, you see IWR in the y-axis, and in the x-axis you see time around the maximum stage of a specific weather regime. You see here the 7 different regimes, and you see time lags of -10 and +10 days around the maximum stage. When a specific regime is active, you can see that the IWR is significantly different from all other weather regime life cycles. Okay, so you can see it for for all 7 regimes. Okay, you can also see that when a regime is active, you can see that IWR is distinct between the regimes, and that the Greenland blocking here in blue has the strongest projection on the climatology. Moving to the cumulative distribution functions, to the CDFs, we now look at the CDFs of IWR, the weather regime index, for the different regimes when a specific regime is active. So you can see that the IWR, again, like I said before, is significantly different or higher at this case for Atlantic Trough, for example, from all other regimes. And when we look again at when all regimes are active, you see that the Greenland blocking has the highest IWR with respect to the other regimes, but they are also significantly different from one another. Okay, so we know that at least the statistical classification of the regimes works for these 7 weather regimes. The second methodology we used is a dynamical systems perspective, okay? And the idea, this perspective focuses on 2 metrics. One is the persistence, so theta in -1, and the other is the local dimension, so the number of active degrees of freedom. Okay, basically, if we want to understand if a specific weather regime transitions into a predictable and more persistent state, we want d and theta to be low. Okay, and if this is not the case, the weather regime is not predictable and not stable when it's at its maximum stage. How do we compute these 2 important metrics? So basically, we look at geopotential height at 500 hectopascal in the ERA 5 reanalysis. Okay, each point in this phase space is a 2-dimensional map of this variable. Okay, we compute the Euclidean distance between this point and all other points in our data set. So in our case, it's 1979 to 2020 in the ERA 5 reanalysis. Like I said, geopotential height at 500 hectopascal. Okay, once we compute these Euclidean distances, we can fit a distribution and define an extreme value. So in our case, it's the 98th percentile around a specific state of interest. Let's say a specific 6-hourly time step of geopotential height at 500 hectopascal. Okay. Within this small region, we compute d and theta. Okay. So d would be the number of options this state or this map at 500 hectopascal can transition into or from. So how many options does this state have to transition? And theta would be just how fast the trajectory moves within this small region in phase space. Okay. So of course, this is if you're not into dynamical systems analysis, this is a bit difficult to comprehend. So this is some intuition on these 2 metrics. So again, let's say we're interested in a specific time step to understand if what is how predictable it is or how stable it is in the sense of atmospheric variability. Okay, so on the green diagonal, you see a persistent state, and therefore theta would be low. Okay, on the purple diagonal, you see a non-persistent state, and therefore theta would be close to 1. Okay, so the atmospheric state changes within each time step. D in this case, so the number of options this state can transition into or from, is 2. If you look at these 4 panels, you see that there's only 2 options this state can transition into or from. Okay, so basically for the whole reanalysis, for geopotential height at 500 hectopascal, for each 6-hourly time step, we have 2 metrics. One is D and one is theta. And according to these 2 metrics, we can say if a specific time step is more predictable or stable or less predictable and stable. But what you need to remember for the next figures It's just that low dn theta is more predictable state and high dn theta is a less predictable state. So what we did is we used the weather regime life cycles as we computed using the statistical classification. And we tested what are d and theta around the maximum stage of each weather regime. And what you can see, which was quite interesting for us, is that at onset of a weather regime, d and theta are relatively high or around climatology. And when we transition, in this case for the Atlantic trough, into the maximum stage of the regime, the circulation becomes more predictable, okay? So this is basically what we tried to answer. And you can see here in these 7 regimes that particularly for Atlantic trough, zonal regime, Scandinavian trough and Greenland blocking, it transitioned strongly into a lower d and theta, so a more predictable and stable state, and which is significantly different from climatology, which is 0 here, okay, on the x-axis, okay? The other regimes also show a transition into a more predictable state, but you can see that it's not really different from climatology. For example, for European blocking, Scandinavian blocking, and the Atlantic region. Okay, again, focusing on the CDFs, we look at D and theta here on the x-axis and the CDF. You can see that this is for the maximum stage of each weather regime. You can see that first they are significantly different from one another in terms of D and theta. And again, that the Greenland blocking has the most predictable or stable state, the lowest theta and the lowest D in this case. So to summarize and conclude, we assess the physical grounding of Atlantic European weather regimes using dynamical systems theory. So we try to compare between the statistical classification and a more, I would say, physical understanding of how flow changes in phase space. What we find is that most weather regimes display distinct and predictable flow characteristics at their maximum stage and unpredictable flow at onset and decay, as we saw in the time series of the weather regimes for D and theta. The agreement between the statistical classification and the dynamical systems analysis provides strong evidence for most weather regimes being physically meaningful. And basically, these findings allow us to use weather regimes for different applications. So we were using these for weather regimes for decades, and there were different articles and studies trying to understand if they actually exist, or we just basically, if we use EOFs and k-means clustering, we can classify anything. Okay, but we want to understand if these are actual physical entities or just nice categorizations that we can use to understand the atmosphere. Okay, and some more details, of course, can be found in this article. And of course, thank you to all the collaborations for this study. And I will just say one final word, which is a bit depressing, but I'm sorry I cannot skip it. As I said, Israel is now at a state of war, and since the 7th of October. And these people, children, women, and babies, are kidnapped to Gaza, and we're doing everything to get them back. Thank you, and I'll be happy to have your questions.
Okay, great. Thank you. So I see that is there a question online?
Yes.
Yes. So maybe we'll give priority to the online question.
It's a very quick question.
Oh, you're gonna read it out.
Yeah. Maybe you can address it yourself. I think people in the room can read it, right?
Well, maybe we're gonna read out loud. Yeah. So Stefano Tibaldi is asking, how much do your results depend upon the prior definition of the regimes?
So basically, it does not depend on it. What we did is we can you hear me?
Yes, we
Yes.
can hear you.
Okay.
Yes, I can hear you and I can see you.
Okay. Basically, we classified the regime statistically, and separately we computed the dynamical system metrics. Okay, and we just wanted to see if around the maximum stage of a weather regime, the flow is actually more predictable or not. So it's two separate analysis. It does not relate to one another. It's just using the classification of weather regimes to test if flow becomes more predictable or less predictable. That's it.
Okay, thank you.
I hope that answers the question.
Okay, thank you very much.
There is one question here. We're waiting for the.
Hi, great talk. I'm Hugo Bordoy, I'm from the University of Trento. I think to kind of follow up the question of Stefanos, I wanted to ask, yeah, if you did this analysis with any kind of K, right now you're using the same definition as the Grams paper, so 7, I think, is the number. I think you would get this deep, whichever K you would choose, maybe not in the same proportions, right? But by the definition of K-means, around the center of those weather regimes occurrences, you're narrowing your phase space, right? Just because of the definition of K-means, right? So I don't know, like just as a question, have you tried with different Ks, different number of regimes to see if you still see this behavior?
So basically, there's the 4 canonical regimes that we tried with that, and we get the same results. Yeah, I think that's. Does that answer your question?
Have you tried with 11 or 15 or whatever?
No.
What is those 7 special in this case?
No, but from these 7 regimes, no, we did not try any other ones. But for these 7 regimes, as you see, basically 4 of them are significantly different from climatology, not all of them. So it's basically the 4 canonical regimes. So this, I think, is the idea.
Jacopo? Maybe I can repeat, whatever. Yes, come.
Thanks for the clear talk. I noticed the fact that the blocked regimes that you showed, the Wheeler blocking is quite different from the other types of blocking. And in the nervous system perspective, blockings are associated with a higher dimensionality. But then the question is, Greenland blocking maybe is not really a blocking. It's more like a waveguide redirection rather than a waveguide blocking. And that's maybe you can explain why the Greenland blocking features is very big, deep into low dimensionality. So it differentiates itself by the other type of blocking. Have you thought about it? Do you think it makes sense?
Yeah, I think it makes sense. Basically, what we understand about blocking is that on the, like, say, wings, like at onset and decay of blocking, that is where we expect the blocking to be unpredictable. Okay, but once the blocking stays in place, then we get a much more predictable state. But what you said, I think it makes a lot of sense. Yeah.
Thank you.
Okay, great. Any more questions? So obviously we are running a bit late, but I think it was really nice to keep a little bit more of a relaxed schedule, so to allow for pending questions. So I would say that maybe we use about 10 minutes for some final thoughts after this first afternoon. And I don't know if there's anybody who wants to start. I do have a comment that might be a naive comment, but the one thing that really caught my attention was the fact that basically in every talk we heard about a different method, which of course, and everybody emphasized aspects, advantages and maybe drawbacks of the specific method, also emphasizing a little bit, of course, that we're looking a little bit at different signatures of the relevant dynamics. But then the question is, and also, which to me also, of course, we're looking sometimes at different aspects of maybe similar mechanisms, but what, again, it's a bit hard to have a coherent picture, and it's also a bit hard sometimes to compare results because, again, different methods, again, as I mentioned, maybe are looking a little bit slightly different or very different things. And so the question to me, is there any hope to harmonize all of these different methods, or maybe no, it's not even a useful idea to have in mind because, again, there is so much diversity. But I thought that maybe one of the hopes was, again, maybe that's my expectations, was maybe to highlight a way to make progress in, again, harmonizing these different metrics. Because, again, going back at today's talks, and this is only the first afternoon, everybody presented their own methods based on different decompositions. And yeah, so I don't know if anybody has a comment, an answer, completely opposite ideas. Yeah.
Also from the
of course, from the
audience.
remote speakers. And again, maybe today's speakers want to say something about this.
Yeah, yes, and Yelka and Kai, they raised their hands at the same time, basically.
Ladies first.
Ladies
so
first.
We're gonna give priority to Yelka.
Thank you, Simona. I really agree with you. But then the methods, I mean, most often we would like the simpler the better. But sometimes the simplest is not really one that provides most informative answer. So I think we have to remain with different methods. Yeah, but you are right. Yeah, we have a large diversity of the methods discussed. I don't have a solution. I don't have suggestion.
Yeah, I agree, but I will not argue that this should be reduced or so. Like every method has their advantage and purpose. It is, however, an issue that a lot of the confusion maybe about trends, certain circulation patterns or meandering or whatever, does result from all these different metrics that can yield different trends in different seasons or different regions. So I guess what is important to always be clear about what exactly is being looked at, and if the purpose is to explain certain types of weather extremes or certain high impact events, then the method should also be benchmarked by the impact relevance, basically. Is that actually the one metric that captures these high impact events, or is it just some metric, but there's only a slight overlap and another metric would be more useful for that purpose? I think that's important to also provide more clarity. Maybe this one question that the media likes so much, whether it's the extreme meandering more or not.
Yes.
I think method and seasons need to be highlighted more, otherwise we never get out of this confusion. We just create an artificial debate which is actually not really there.
Were people online able to hear? No, not really.
I think that the very summary of what Kai was saying is that
it really depends on the context, and we have to be precise of what we are looking at, right? That's it. Maybe.
Yeah, precise about accurate about our definitions, what exactly we're looking at, and that the diversity is representative of an actual physical diversity that we want to keep, right? That's, yeah. And then again, be careful about talking about trends, and again, be accurate exactly, because otherwise diversity in trends and seasons really arise for actual differences rather than based on, yeah. Okay. Emanuele, can you please, sorry, it's just so that we don't leave people, if you can please come so that we don't always have to put our own subjective interpretation into the summary.
Which is
so
always
that
subjective.
always subjective, so that people online can participate to the discussion.
I mean, a comment on, let's say, homogeneity, you were saying, right?
Harmonizing.
Harmonizing, yeah, sorry, yeah, okay. So what does that mean? It's also a question. Is it about just removing the diversity or not? And in that removing the diversity, I don't think it's the case. It's more about getting an understanding of when we ask a given question and we use different methods, whether we can get different answers. So I think this is more something that could help. And this goes a bit beyond, it's a bit different than metrics, because for a given a metric, you can use different methods to look at the same metric. But yeah, given a question and a metric to characterize that, to address that type of event, does using different methods with different answer? If so, that's an issue. And I mean, it would be interesting in principle, but of course it requires a lot of work, like having a sort of inter-method comparison project, right? Where you can ask a couple of 4 questions and check out how the answer are. I don't know if you're envisioning something in this direction as an outcome of the workshop, some analysis. Yeah, that's all. That's all.
Yeah, so I don't know, to answer, well, it's not really answering your question, and I should, I admit my ignorance, and I haven't kept up with the literature, but for instance, one thing that comes to mind is Hadley cell expansion and Hadley cell strength weakening, and there are many different metrics, and several review papers have looked at the different trends that come up from the different metrics and trying to explain why sometimes you have differing trends, because again, they are looking at, well, those might be related to things that, for instance, reanalysis, when we look at observations, certain things they do well, some other things they do less well, but also trying to understand why, if you look at a different metric, why the answer might be different, whether that is based on, for instance, circulation changes in the net precipitation and things like that. So that is, again, not to, again, I'm guessing that similar things have been done, similar intercom, intermetric. Yeah. I don't know if that's, again, as you're suggesting, I don't know if that would be a useful outcome of this workshop. I don't know what that is. Yeah, sure.
If I may add on this, when I started thinking of this workshop, I think that the main question to me was, is there a pan mid-latitudes dynamics really existing or not? Do concurrent heat waves have some physical meaning, or is just statistics? And I think that when it comes to methods, it is really important to also to give ourselves an underlying physical question that is meaningful. And I don't have an answer for that. Actually, I would like to listen from the people in the audience about that. As I mean, we maybe have been working on this stuff from several points of view. I don't know. Yeah.
Lenka.
Is this one work as well?
I think
no, it's only this one
one
because it goes into the.
Yeah, so from the kind of mid-latitude dynamics, I would say there are some phenomena that have been studied from lots of different angles, like the jet stream shifting.
Yes.
What's happening with wave breaking, what's happening with wave packets, what's happening. You know, there are different metrics and different ways of describing the dynamics. Blocking is another example. There are different metrics for that, and there are inter-comparison papers that look into that. With heat waves, I'm not
Quite sure.
too sure about that, but I agree that there should be, like what Karen was saying, there should be a variety of metrics to try to explain the mechanisms, because that's, I guess, what you just outlined you were interested in. And the best way is to, I mean, from a completely unbiased point of view, it's best to look at the idealized models first and try to
totally unbiased.
Very unbiased. And try to look at these metrics so that you have a baseline simulation, and then try the different metrics and see what they actually look like with the same data, and then try to apply it for more complex models.
Yeah, I agree. Yes. From a totally unbiased perspective, absolutely. Paolo.
Yeah, sure.
So I also agree that regarding the various diagnostics approach we have seen, it is good to keep all of them, because maybe there is a diagnostic which is suitable for something and another one which is suitable to investigate something else. One thing that probably can find some common ground is that, so we talk about heat waves, wave dynamics. One useful thing when we look at this phenomenon is really to partition between what is conservative waves and what is non-conservative. So which kind of forcing may act on the wave trends, heat waves trends. And in this way, Tiffany before was saying, you cannot really escape from the full PV inversion of the state. And this is actually a tool that nowadays is missing. A few people have done it. They put a lot of effort. It's still very computationally inexpensive. And we saw, for example, what Jacopo was saying before. That's like a trick to overcome this computationally expensive problem and to basically make this method more affordable, such a PhD or a postdoc can compute it. But I was wondering if, for example, 5 scientists or even 10 can maybe put their effort together and write a tool that is computationally efficient and can actually recreate this reference state given a wave pattern. I think it can be done actually. So in that way, you can basically make a step further compared to a diagnostic and even being able to make some quantitatively correct arguments, at least from the theoretical point of view. But nowadays, I haven't seen such a tool. I know that, for example, Claire Huang, who was a formerly PhD student of Noboru Nakamura, did it for the quasi-geostrophic theory. Christopher Porster did it with his rolling window. So all the methods, they assume one assumption for the method itself to be amenable to data and to be computed. But the full PV inversion is still missing, and this, in my opinion, could be a common ground to start to be able to make quantitative arguments.
Sure.
I think I saw that in the tropical world that there are some tools which are shared between researchers, like Oriadus was part of this, I don't know what it's called. But there's like a software package which has all of the kind of most common diagnostics there, and if in our case it would be useful to have some sort of very simple unit test in there for those diagnostics. And yeah, I really do agree with Paolo that having some sort of shared code, because I know other people who have worked with class code and they've adapted it in different ways, but then what happens to that code when they graduate?
Yeah, it's not anymore maintained or then.
Agnieszka?
Yeah, maybe just one statement is that the extratropics, geostrophic framework are less suitable than tropic.
Nadelka, sorry, we cannot hear you very well now. Maybe it's something wrong with the mic.
I will type it.
No. Okay, you wrote it down. Nadelka wrote, standing challenge is that tools that are suitable for exotropics are less useful in the tropics. For example, PV and Kelvin waves. It's also a very good point, actually. But yeah. But the thing is that if you implement some, if you find some case studies or at least some domains where you're testing a set of methods, and then you can use different sets of methods on different domains. Is there still a way you can come up with a, say, integrated interpretation, or things are not talking with each other? I don't know if I understood myself, but yeah.
So I think Jacopo had a...
Hi, Jacopo.
First Jacopo, then Kai, sorry.
I'll just a follow-up actually, Valerio, on your point of the concurrent heat waves, because this research on this interest towards the connection between Rossby waves and heat waves arose because at a certain point, all of a sudden, heat waves start to multiply and appear everywhere at the same time during summer. And then there will be a talk, I think, tomorrow by Clarissa Rogers, right?
Yeah.
And it's about the paper about the shows indeed the sixfold of increase in the occurrence. It's you. Sorry. I know you because you're a co-author, but I didn't know you. Exactly. So, and if I'm not mistaken, one of the results of the paper is that the main driver of that is the thermodynamics rather than the dynamics. And therefore, of course, this doesn't mean the dynamics is not at all relevant, but then we have to wonder, okay, but what is then the dynamics behind, if there is one, we have to first find out which one it is, besides normal Rossby wave packets absorbing just more warmer air than usual. And maybe Kai has a comment.
This is CAS work really, but maybe that's, I guess, a case where you really have to be specific because the changes in the trends are mostly driven by thermodynamics, but then the phenomena themselves were categorized by circulation patterns, basically. So I think that's kind of what can be said. Like the increase in concurrent heat waves is mostly driven by background warming, but likely under the condition of specific circulation patterns. So the circulation patterns don't increase in frequency, but they still need to be there to drive these concurrent events.
And which circulation patterns are they?
This is a wide range, right? We cluster them as.
I asked this question a bit directly because we know that when we know about Rossby waves or Rossby wave packets, and we know how they look like. They propagate. They're waveguide, but then they somehow, they are, what to say, these Rossby wave packets are just Rossby wave packets, are the usual ones, and in these circulation patterns that I discussed in the paper are more like certain global patterns, if I'm not mistaken, right? And these ones, they're then at least personally, I struggle a bit to see them on a weather map sometimes, because we know how. And so, from the perspective of the most parsimonious solution, like sort of Occam's razor somehow, I would be more like, okay, then probably it's Rossby wave packet. And this is maybe. And then when we go, okay, but then there is a special waveguide for that, and then okay, there is a different type of waveguide, which is not the usual Rossby wave packets with a special type of waves in them. And this is a bit, maybe it's an opinion, of course, but you're here to discuss with. So it's a bit difficult to visualize these different waveguides, which requires a different methodology. So, I mean, yeah. So, but maybe it's the right place to have this type of discussion.
Maybe just a quick comment on that. Yeah, I think that refers to the time scales under which you look at the circulation pattern and also the concurrence, because that might not occur on a daily basis, but within 2 weeks or so. And then if you use that as the time scale for your circulation as well, you do see certain patterns emerging. If you go further down to the more weather scale, hourly or daily data, then you see these other features, right, that you have discussed, also this recurrent Rossby wave patterns that Olivia and Matthias looked at. So it's a metric question, right?
But it's also a physics question, because depending on the type of wave we want to look at, then we ask ourselves different questions. So it's a problem with like the metric, the variety of metric, then it comes back to the physical questions you want to answer. Use this metric to answer to, and that's actually was the connection was with your comment.
Sorry, Cassandra.
I just had a response.
Sorry, Cassandra, could you ask? Yes, thank you.
As much as we can, we move closer to the mic.
Yeah. So with the circulation patterns, there was the thermodynamics was the overwhelming driver, and you sort of saw in like when the heat waves did sort of start to just occur every single day, and it was thermodynamics, but the dynamics drove where they were occurring to some extent. So it meant that if you took out the dynamics, they would either exacerbate the thermodynamic impact in some areas or diminish it in others. So it was still was very small compared to the overall trend, but there was some dynamic influence. And then on the bit you mentioned about the clustering, so that was just, what was it, 20 patterns, and so everything is split into one of those patterns. So it does mean some of them don't necessarily match the patterns very well. So it's a lot less specific than if it was looking at like Rossby wave packets in particular locations. So yeah, I guess then you can use more circulation patterns, but then you can just get a bit too much and it's a bit too busy. So it was nice that that method let us group everything into 20 nice packets, but there would have been limitations with that.
Maybe related to this issue of the circulation patterns. I mean, when we did this, I mean, weather regimes classification, I mean, we had in mind that this analysis should have been translated into, I mean, looking at climate change scenarios. And the first thing I thought was, well, if I classify the weather regimes like these, I mean, whatever, it's not important the way you classify them, but if you do that in an unperturbed setting, would they still work in a climate change setting? And that's why in the end, we chose as a metric the frequency of that same weather regime across time or in different populations, whatever. But this doesn't mean that it has to be like this. I mean, it can well be that, I mean, you change the set of circulations in different settings, but then you have to decide how you measure it, or I mean, how this is representative of the changing background state, so to say. I think this increases the level of difficulty by one step. If all what we are talking about is translated into the world of climate models, projections, and climate change. Okay, that was too much too late.
Not too much, exactly. So yes. maybe this is a good point to call it a day, also because we have still one full day and half a day tomorrow and the day after tomorrow. So thanks everybody for great presentations, and I think a great start of our discussion. Some of tomorrow's in-person presenters are still here, and so I received a comment that sitting doesn't make for very engaging presentations, especially because if you sit in a corner, people cannot even see you, and so our recommendation would be please stand up. The online, the hybrid setting maybe doesn't, it's a bit confusing, but one suggestion that maybe, of course, our presenters can take for tomorrow is
I think this works as a pointer as well.
That
but
works
I did
as
not
a pointer.
check, so
We did not check, so we need to do our homework. And we'll do that. So again, thank you so much, and we'll see you tomorrow. We start at 9 a.m. And presenters either come here and upload your presentation already tonight, or send it to us through email, or come tomorrow a little bit earlier than 9.
Yes, I received that.
You received it. Good.
Yes.
So when did you get married? No, because you said that your parents and then said, yes, my husband now. So yeah, you mentioned that they're in France. Yeah. French, and you guys met in California? In LA. Yeah. What does it do? It's terrible. It's a mess. But it's real good. I thought. So is everybody like normal in terms of going into the office? Or no, it's still yeah.